What's going on?
So all the participants are actually requested to mute their mics. Please ensure that your mic is off.
Hello. Hello. ನಮಸ್ತೆ. ಅದರ ಕಲ್ಕೊಂಡು ಹೇಳಿ ಹೇಗಿದ್ದೀರಿ? ಫೈನ್. ಈಗ ನಾನು ಕುಶಾಲನಗರದಲ್ಲಿ ಇದ್ದೀನಿ ಸರ್. ಊರಿಗೆ ಹೋಗ್ಲೇ ಇಲ್ಲ ನಾನು. बहुत सारे लोग ये मोबाइल
Hello. हम्म आप पारे सर से बात करो, अभी मैं थोड़ा बिजी हूँ। पारे सर से
Hello, Dr. Ashok.
Yes, sir. Good morning, sir.
Yeah, shall we start the presentation?
Yes, sir. एक second.
Okay.
एक second, sir. Subodh?
Yes, sir.
Subodh?
Yes, sir.
You can start now. You can start. Proceed further.
Yes, sir. A very good morning to all our viewers. I, Subodh Trivedi, would like to welcome you all to the second day of our faculty development program on the topic Recent Advances in Mechanical Engineering. Today's session focuses on the topics Laser Assisted Manufacturing, Macro to Micro. And we have as our guest speaker Dr. I.A. Palani. Sir, you are working as an Associate Professor in the discipline of Mechanical Engineering, IIT Indore. After completing your doctorate from Indian Institute of Technology, Madras, you worked as a postdoctoral research scientist in Graduate School of Information Science and Electrical Engineering, Kyushu University, Japan. You have developed mechatronics and instrumentation lab at IIT Indore. Your area of expertise includes laser-assisted surface processing, micromachining, smart materials, and shape memory alloys. You have published more than 100 international publications and have filed 6 Indian patents. You have executed projects from different funding agencies such as DSP, DAAD, JSPS, DRDO, MHRD. You have closely worked with industries such as Volvo Eicher, John Deere, WABCO as technical consultant. You are a member of SPIE, Indian Laser Association, Institute of Smart Materials and Structures. You are the founding head of Metallurgy Engineering and Material Science at IIT Indore. Currently, you are heading the Mechanical Engineering discipline at IIT Indore. Sir, we welcome you. I would now request you to please start with the session.
So good morning to one and all. So thank you very much for giving me this opportunity to present my work related to this laser processing. So I should thank Dr. Ashok who has invited me for this presentation. So I think I am, you could see my slides. Okay, so the topic which I will be discussing today is something related to laser assisted manufacturing, basically from macro to micro. So here, as far as this presentation is concerned, so this is the overall introduction to my lab, so which already people have given an introduction. So we have a good facilities related to laser. So before going into this topic, so in today's lecture, we will be discussing about the different, we will discuss with respect to different case studies which we have solved in our laboratory for different applications, which ranges from macro to micro, with the field of laser assisted processing, which we are going to discuss in detail. So we all know laser is an advanced tool. Basically, if you try to look into its history, so it was first developed by Theodore Miming. So later it has its own shape at different levels, and India has its own contributions in developing this carbon dioxide based laser. You know, Professor Patel from Pune has developed this carbon dioxide laser, which are being used in different applications, different heavy applications, etc. So apart from that, for a micron level or for a micron control over it, so basically there are other types of lasers such as India lasers, then gas lasers, dye lasers, etc., which are of different. So basically now here comes a question. So you have a variety of applications. Basically we will be looking into variety of applications. When we try to look into variety of applications, which kind of laser basically suits? So that is quite a tricky question. Okay. So for that we need to understand our requirement, and second thing is we also need to understand the mechanism of laser material interaction on any. Okay, so first if I try to look into it, so first we will be discussing about this laser material interaction. So we all know that any material if we take, when a light is falling on the surface, you get different phenomena. One is transmission, absorption, and then reflection. So as far as absorption is concerned, we know when a beam is incidentally on the surface, the beam, the light beam, basically the photon which is being incident on the surface is being absorbed. So this absorbed is being transformed in the form of heat. Like in a simple step, I would say. So we all know about this atom and an atom. So in an atom, we have a proton, neutron, and an electron. So when the light strikes the surface, so basically it disturbs the electron. So the electron tries to give out certain amount of energy to come back to its stable state. So that energy is basically in the form of heat. So this concept we call it as thermionic emissions. Basically, we get it in the form of heat. So basically, to govern this, or to look into the phenomenon behind this, so you have a different equations. So one major equation which I would like to focus about is called as this Beer-Lambert's law, which is nothing but I equals I naught xp minus alpha into x, where I naught is your top intensity and alpha is your optical absorption coefficient, x is along that. Like if I try to explain it in this way, for example, I have a laser which is being falling on the surface, so I am just discretizing it into different layers. So the top layer is of it, and then there will be a transfer of what I would say is transfer of heat towards the surface. So thus leading to a transfer of the energy throughout the layer. So this is called as a Beer-Lambert's law concept. Okay, so here in this case, the major contribution comes from this optical absorption coefficient. So as far as this optical absorption coefficient is concerned, so this optical absorption coefficient basically changes with respect to different material. Like you take a wood, the optical absorption coefficient changes. Whereas if you take a glass, optical absorption coefficient changes. So basically that decides the transmission of the light. For example, I take a glass. So it doesn't transmit all the light with all the set of wavelength. Basically, certain amount of wavelength are being captured by the glass, so that in such a way that it gets absorbed and sometimes it may get heated up also. So with this as a fundamental, so if I try to look into this laser material interaction,
we can't see the slides. We can show the slides.
Any issues are there regarding the slide share?
Yeah, there is a slide is only, it is very small. Can you show it? We need
Dr. Ganai, please see the matter.
Hello?
Dr. Ganai?
What happened? It is visible.
Yeah, it's visible, but it is very small. It's just small only.
No, I think I have kept in a full screen mode.
It is not on full screen, sir.
No, it is on full screen.
Yeah, it is full screen.
Okay. Now we can see. Now it is okay.
Okay.
Okay, sir, go on.
Okay. So I think there is no issues. So now, as far as this laser material interaction is concerned, so you basically classify into 4 different categories. So one is something kind of heating, where you are just incidenting the laser beam into it, and there is a mild amount of heat which takes place. Where like for example, we might have heard about this laser cleaning, where you don't require a high amount of heat. It requires a mild heat so that it removes the moisture. Second thing is surface melting. So as far as surface melting is concerned, we all know a laser is being interacting on the material. So there will be some kind of melting which happens. Basically, it is something like you are heating the solid and it comes in the form of a liquid. And the third one which we talked about is something related to vaporization. So as far as vaporization is concerned, so you are just irradiating with the laser. You are irradiating in such a way that this liquid pool gets boiled, and finally you end up in some kind of vaporization. And then the last is something called as plasma formation. So plasma, we all know, it's a 4th state of matter. So basically, as far as in this case is concerned, so you will be irradiating the laser on the material. You heat the material in such a way that the solid becomes liquid, the liquid becomes gas. Further, when you try to expand, it forms a plasma where there is a plasma expansion. So any laser material processing you take it, that will fall under either of these 4 categories. Sometimes there is a chance that there might be an hybrid cases, but any material processing related to laser you take into this. So now, with this as an idea, if we try to go one by one, so this is something related to laser surface melting. So as far as in the surface melting is concerned, so we have 2 different phenomena. One is a heating cycle and another one is a cooling cycle. So I just incident the laser light on it. So there will be a certain amount of increase in temperature where there will be a surface melting. And when I try to quench it, it results in cooling, which will result in surface melting. So in a micro level, if I try to look into it, most of you might have heard about this concept called laser annealing. Or some people might have heard about this concept called laser hardening, which is nothing but you are recrystallizing the material. So when you try to recrystallize the material, so you are just heating it and you are just quenching it so that you are just creating some kind of nucleation site within your structure. So this is one good example. Another example is related to surface vaporization, where you are just heating the material and where there is a surface melting is there. When you try to heat it, so this will give you a better clarity. What are the different zones of laser-based processing which happens? So one is related to laser heating, another one is related to laser melting, and the third one related to laser-based evaporation. So beyond this evaporation, there will be a continuous degradation or continuous vaporization of the material. Okay, so this is an example of mild heating, where you are just insulating a laser beam and the heating happens in such a way that you just heat it and then you just clean the surface. Okay, so now with this as a concept, let us go into the different case studies where we will identify a problem and how we have approached the problem for different approaches. So the first case study which I would like to project is something related to laser handling and texturing of solar cells. Okay, so we all know about the solar cells. So solar cells has NLP junction. So, but the major challenge in this is basically here we have taken a particular application where we are planning to convert a low-cost amorphous silicon into a high-cost crystalline layer. So what we do is basically, so this amorphous silicon, we all know, the whatever solar panel which is there on your calculators, those are of low cost. Basically, it won't have any crystal structure in it. Basically, it has an amorphous phase. So because of that reason, the efficiency of these solar cells happens. So in order to improve the efficiency, so we can go to one is to induce a crystalline. So when you try to induce a crystalline, so it has an amorphous phase, but still you are just completely eradicating the amorphous so that you are reducing a crystal structure in it. Second thing is, what we thought is we will induce some kind of textured pattern on it so that you can improve the efficiency of it. So this is the kind of NNP layer where this is the overall structure of the solar cell, and so that when the light falls on it and when you have a polysilicon textured pattern, you get a multiple internal reflection into it. With this multiple internal reflection, you can improve the efficiency of it. So that is an interesting part with respect to this case. So my requirement is something like, so I need to convert this amorphous into a polycrystalline so that this amorphous has a capability of retaining its optical property, as well as when I try to induce a polycrystalline in it, it has a capability to have an improved efficiency of it. So for that, one major thing you might have thought of this, just my objective is just for recrystallization. Why should I not need to go for some kind of furnace annealing technique? But the problem is, when I need to go for a furnace annealing, I will be heating over the entire area. I won't be having a control over a particular crystal structure, which is being avoided. So here in this case, so this is a laser handling unit which we have employed in it. So in this laser handling unit, basically for our experimental purpose, we took two different types of amorphous layer. So one amorphous layer we just deposited on silicon, and the other amorphous layer we deposited on a p-type gold layer. So basically both were of same nanometer thick. And then we use an Nd:YAG laser. Basically, it's a fused Nd:YAG laser. So basically, these lasers have a capability to have three different wavelengths. That is 355, 532, and 1064. So basically, based on this wavelength, your optical absorption coefficient can be like for any material, optical absorption coefficient will be the same. But with respect to the different wavelength, the value of the optical absorption coefficient gets switches. So like that, for example, if I need to select a material, if I have a material, it's better to do a UVBA spectrum before I treat with the laser, so that when I try to do it, I will get at which area exactly my optical absorption coefficient is quite high, and based on that I can map my wavelength and I can just switch. So here, just for an understanding, so we are trying to report some of the different types of wavelength which we have used and how it is being used for different applications. So in order to measure the temperature, because we all are more interested in this temperature, we went for a technique called as time resolved reflectivity technique. So this time resolved reflectivity technique is quite interesting, where this is my laser which I am using it for irradiating it. I am using a helium neon laser. This helium neon laser strikes the surface of the material. So this is a low energy laser. Basically, whichever you use it for your pointer. So the same laser I am just using it over here. So this will be irradiating on the surface, and whatever reflection is coming out, I am trying to couple it with a fiber coupler, and then I am trying to measure. So what happens is, like I have a material. So when I'm just irradiating with the laser, so we have seen the melting and the vaporization. So when the melting and the vaporization happens, basically the reflectivity of the probe laser, so this is what we call it as a probe laser, gets changed. So with respect to that reflectivity, you can understand where exactly your a reflected signal happens and what is your window, which is working on. So this image will give you a better clarity. So this is with this SEM micrograph image where this is the SEM image for an untreated region. Slowly I am increasing my laser fluid. So this is at 230 millijoule per centimeter square, and this is at 390 millijoule per centimeter square, and this is at 440 millijoule per centimeter square. So at 390 millijoule per centimeter square, you get a small micro granules, and at 440 millijoule per centimeter square, your micro granules, basically your crystal structure slowly gets improved. The reason behind this is here you have a liquid layer. So this liquid layer is being quenched. On the other hand, here your boiling point is quite heavy, so that you have quite a good amount of crystal structure that's being made. So to correlate this, basically this time resolved reflectivity results are over here. So basically this is your region of melting and this is your region of vaporization. So in this region of vaporization, you can understand. So basically there is a dip in the curve, and whereas at the region of melting, you can have an improved reflectivity because of the molten pool of the material which is being available over here. Okay, so next we did some electrical characteristics, the optical as well as with respect to electrical characteristics. So we did some Raman spectroscopy to understand the behavior of the crystal structure. So basically, so wherever we had a better mapping, so we could get a better crystal structures. And this is some kind of resistance measurement which we perform. Basically, this resistance measurement would be helpful for us to understand how the resistivity changes with respect to the different. So this is an Hall effect measurement, basically more towards an electrical characteristics, which gives me a better clarity how the crystallization is being induced and how it has its own effect towards solar cell applications. Okay, so these are some of the XRD measurements which basically helpful for us to understand the crystallite behavior which has been happened with on the amorphous region. And just to give you an overall picture, so we have used the same energy at different wavelengths. So this is with 355 nanometer, this is with 532 nanometer, and this is with 1064 nanometer. So when you try to incident the energy, so you can have a control over the depth. So this is along the depth of the material, along the cross section, how the heat transfer was there, and this was along the temperature. So along the depth of the material, you can see how the things were getting transferred and how the crystallization part we are trying to look into it. In fact, we did some simulations to understand the crystallization characteristics in detail. Okay, the next concept what we are talking about is something related to laser-based surface texture. So this surface texturing is something like, so already we have discussed, like I have a panel. So one thing is I need to induce some kind of annealing. Another one is I need to induce some kind of texture so that I can have the input reflectivity coming out. Okay, yes?
Hello, sir.
Yes, sir, please.
The PPT not visible, sir.
Actually, sir, there are two windows are there. Okay, so one window will be my video, another one will be a present. If you click that, obviously PPT will come.
Good.
Could you able to see?
No, sir, no, sir.
Yes, participants can individually select that option actually. This is not from my side.
Actually, there will be two options. In my name, two will come. So one is for presenting.
Yes.
So once you click that, you can see the presentation.
Because if you go through the YouTube streaming link, it is fine. You can, if you are having problem, then you can go to their YouTube streaming. Okay.
Okay. Shall we to the next? So basically, so here we are trying to look into some kind of texture pattern. So this texture pattern will be helpful for me to understand the behavior and to study the multi-resolved reflectivity in these kind of crystals. Okay, so basically, so these are some of the texture pattern which can be created and which will improve the efficiency of it. Let me just show you some texture pattern which we have developed. So these are some of the texture pattern which has been generated using a chemical etching. But the major aspect of chemical etching is, so the more to do the chemical etching, there is a chance that you may end up in some kind of issues related to.
No, it's not visible.
Hello?
The slides are not visible, sir.
Sir, actually there are two options are there. You need to click that option where I am presenting. Hello? Is it the problem with all?
No, sir, it is visible.
Okay. Yeah.
Visible and clear. No problem.
Okay.
So why are you disturbing in between? Yes, sir, visible.
Can see this slide.
See, please select Palani AI presentation. Okay, please click on that. Only then you can be able to see.
Sir, sir, 1 minute, sir. Sir, yesterday, Palani sir means Palani and Palani sir is nearby one. But today, Palani sir presentation one place is there, another one more place presentation is there. All of you, sir, you can get it. Now only I got it. Okay. Thank you.
Wherever the presentation is coming there, you can just pin it, sir.
Okay, thank you. Okay, so basically, so we can just talk about this texturing part. So as far as in this texturing is concerned, so basically you will be using a laser beam. So with this laser beam, you can create some kind of crust and trough. By creating this crust and trough, so there you can infuse the light, so that when the light falls on it, you get a multiple internal reflection within this laser texturing part. So that is what the idea behind this. So this will give you a better clarity how exactly a direct laser texture appears and how the light falls on it and how a multiple reflection affects on this. So there are different types of texturing which has been done till date. So one option was they go for some kind of chemical etching. So with respect to that chemical etching, then the laser is being irradiated on it. So when the laser is irradiated on it, so you get such kind of patterns, and using these patterns, the light falls on it. Because of this light formation, you get a continuous efficiency improvement in efficiency. So here we have attempted one thing, something like we use a homogeneous beam, and by a homogeneous beam we could create such kind of pillars kind of structure, so that these pillars kind of structure would be helpful for us to improve the efficiency of this. So this will give you a better clarity. Now, so what we thought is, since we have already done an annealing, so we thought of employing such kind of methodology called as beam overlapping. So this beam overlapping will be helpful for me in such a way that this beam, when you try to do a beam overlapping with 50% and 90% overlapping, so you can have an improved in the crystal structure, as well as you can have an improved in the texture property of it. So when I try to look into this mechanism, basically you might be asking a question how it is happening. So there is a concept called Maragoni convection. So this slide number 37, I'm currently in slide number 37. So this will give you a better clarity, where I have a layer where I'm just irradiating with the laser. So you have three different regions. So first is your irradiated spot, second is the second irradiated spot. Basically I'm just moving the beam. So when I try to move the beam, so this is your first region, this is your second region, and this is your third. So the first region is already getting crystallized, the second region is an overlapping region, and third region is an irradiated spot. So what happens is, because of this, there will be some kind of Maragoni convection. Basically, you are just trying to change the temperature gradient along the boundary. When I try to change the temperature gradient along the boundary, so you end up in some kind of Maragoni convection. So that is nothing but, like, let me just explain you with a simple example. I take a bowl of water. So I just put this bowl of water inside the freezer. We all know the freezing happens from the surrounding to the center. So that is the reason, sometimes if you observe the center, there might be a small peak of ice, small hint of ice which will be happening. That is because when you try to create a gradient, or when you try to freeze it from the outer boundary, you are just pushing the liquid end towards the end, and when you try to push the liquid towards the end, you end up in such kind of peak. So the same mechanism we are following over here. So instead of, so we are not going for any freezing. Instead of, we are just trying to manipulate the temperature gradient in such a way that you have different regions or different parameters. So when I try to insert such kind of different parameters, you end up in such kind of Maragonic convection. This Maragonic convection, when I switch off the laser, so it will induce in some kind of crystallite. Basically, some kind of capillary force will happen on, and because of this capillary force, there is a kind of coagulation, and finally you end up in. Okay, so with this as an idea, so your input parameter is something like your spot overlap, and your output parameter is your texture. So more you do your spot overlap, more will be your textured peak. So that is what our finding is. So basically here we are going for a 50% overlap, and here we go for a 90% overlap. So the more we close, more the percentage overlap we go, so the more we get the textured peak coming out of. So we just try to evaluate it. Even we did some theoretical studies to understand what is the temperature gradient along this interfacial region. So when we try to understand this temperature gradient along this region, this will be helpful for us to give a better clarity how the temperature gradient exists along the zones, and with respect to these zones, how was our reflectance characteristics was getting affected. So this we did some photovoltaic properties. So basically we all know that in as far as sunlight is concerned, you have infrared region and you have a visible region. So we checked the characteristics along the infrared region and the visible region, and this is the percentage reflection from the surface, where we could understand that there is a reflection getting down, and here also a reflection getting down at 90% over. Okay, so then we thought is basically we were using a Gaussian beam profile. Normally any laser if you take, so your profile is something like this. So this is your conventional profile which you do. So the major drawback with this Gaussian beam profile is you are focusing your energy, 80% of the energy over here. So what we thought is we want to make it a uniform beam, like most of the manufacturing engineers who know. So we there might be a question from you. Laser normally it strikes in a single spot. So, but for example, if I want to cover it over the entire area, it is good for me if I convert that laser into the form of a line beam. So if I try to convert it into a line beam, then I can go for a mass production. So for that we use a bi-beam shaper system. So basically this is a commercially available system which we use to check how the beam looks like, and we also studied its behavior towards the different applications, like towards the annealing characteristics and the texturing characteristics. But as an alternative thing, so what we did is, see, this is not possible to get an optics for rupees 1 lakh or something for getting this line. So what we did is we went on a system which we called as a cylindrical lens system. In fact, that I will be explaining in my upcoming slides also. So where you take, you just merge your convex and your concave. So that is nothing but you take a simple burette or a pipette which is used in the chemistry lab. You cut it into half and you just pass your light in between this in this burette or pipette. So what happens is this burette and pipette is a combination of convex and a concave. So when it is a combination of convex and concave, your spot will get enlarged and it becomes a line. Now you need to do some kind of arrangement, lens arrangement in such a way that you can get a uniform. In fact, we did some texturing related to that I will be discussing. We did some underwater texturing for a high energy application, which I will be discussing it in detail. Okay, so this is something related to microprocessing of laser. Okay, some more microprocessing which we will be discussing. Next, we will think about something related to macroprocessing, something called as laser nitride. So till this, is there any doubts or is there any clarification? Just a take home, just to summarize you, we looked into this laser material interaction on the material. So we also looked into how the laser tried to pass through the material, whatever processing you do. So we took on 4 different categories. One is something related to heating, vaporization, melting, and plasma formation. So this, and then we took a case study related to laser annealing combined texturing for some kind of solar cell applications, where we studied about the influence of different process parameters. We studied about the melting characteristics using time resolved reflectivity. Then we also studied about creating a texture, a positive texture on the surface. So for that, to create a positive texture, so we can just tune the overlapping percentage, so that overlapping percentage would be helpful for us to create a positive texture. And then we also had something related to manipulating the beam for a large area or for a mass production. So any doubts or any questions on this?
Sir, hello sir.
Yeah, please.
Can you audible, sir?
Is by laser can able to do, right?
Sir, it is audible, please.
Audible, sir? Can I speak?
Yes, sir. Yeah, please.
I actually, so we want to develop the laser heat treatment concept in our conventional UG boys. What may be the approximate expenditures to incur for that, sir?
Actually, see, I will tell you one thing. Currently, laser is so cheap. Like if you are looking at for UG, even in Amazon, you can get a laser for 75,000 for with the market. Okay, so if you get one unit and if you just teach your student how the laser production is happening, with that even you can cut thin sheet. Basically, I remember that machine is mainly meant for cutting wood, carving wood, marble wood or something. Okay, so that will be helpful for you to demonstrate to your students how the laser transformation happens. But the only thing is they don't give any safety goggles. So that you need to buy it separately. That you need to take.
So thank you, sir. Regarding any doubt, I can contact you, sir. Mail.
Please.
Thank you.
Okay. So can we go to the next session, or is there any doubts?
Hello.
Sir, surface waviness by laser, it is possible, right?
What, sir? I couldn't get you. Surface
waviness.
Surface waviness is possible. Actually, in fact, in our case, we have done a surface waviness in a micron level. Okay.
Okay.
So given now we are trying on a macro level for to
Okay.
create a positive texture on a cutting tool. So that is
Okay.
possible. That is
Right, sir. Can you share your email ID and
sure. Yeah, sure. I will just text my email ID and contact number, so you can.
Thank you, sir. Thank you so much.
Okay. Now we will go to the next.
Hello.
Yes, sir. Please.
Sir, as you said, you have this laser texturing machine in IT Indore. Sir, do you have any picture of that machine?
Okay. Actually, one machine which I'm just scrolling my slides now. Okay. So the one machine which I have shown over here, I will just show you. So this is one machine which we are having basically, but basically this is a pretty old machine. Now we have upgraded our machine with some kind of laser spectra unit. Okay, but this machine is available.
Sir, as you told, sir, you are working in this area, sir. Can you explain any optimization parameters so by which we can know which parameter is affecting more in case of the changing the surface property side?
Okay, so actually in this case is concerned, in my lectures till now, I have been talking only about the pulse laser. So as far as pulse laser is concerned, laser fluence is a major parameter. Okay, so if you see in my presentation, you might have seen that there is a parameter called millijoule per centimeter square. So millijoule per centimeter square means joule means we know that there is a power per second. Okay, so the amount of energy which is being incident per second is the major parameter. Second major parameter which I would like to look into it is, so this, since it's a pulse laser, there is a parameter called frequency coming into picture. So the laser which I am using is a 10 hertz frequency. That means in a second 10 pulses will become. Okay, so if I need to overlap a spot, basically it means that I need to move it in a particular direction in such a way that in one shot I get this. So these are the two main parameters with respect to pulse laser. Whereas if I go for a continuous laser, basically your laser irradiation time plays a major role. And obviously, when you try to take energy into consideration, millijoule per centimeter square, that centimeter square is nothing but your irradiation spot. So that will be taken care. So the major parameter is your laser fluence, another one is your laser irradiation time. So you need to optimize that for your application.
Sir, there are a lot of methods for surface texturing, but can you explain in what sense laser surface texturing is means important as compared to the other processes?
Okay, see, actually, in couple of my slides, I have shown that about chemical texturing, etc. The problem with the conventional texturing is basically it is something like it goes on a large area. It is very difficult to focus for a particular location. Like, let me just give you this example. In this case is concerned, my texture should not happen throughout the area. It should be in some particular region. So in those conditions, if I go for a chemical, I need to create a mask, I need to create a thing, and I need to work on it. Whereas with this, I can just focus it and I work it. That is one advantage which I feel. Second advantage what I feel with this is, see, if in this presentation, if you see, I have coupled two processes, annealing and texturing combining. Okay, so what I'm doing is, in a single shot, whatever is my objective, I am getting that. So I don't need to go for two-step process. In a single-step process, if I try to overlap at 90%, then I can do the annealing and texturing combining. So that is one advantage which I feel with laser. But sir, actually, since I don't think that I am selling my product, this here there is a disadvantage is also there, because this controlling this texture at each and every spot is not uniform code. Basically, I should say that the repeatability gets changes unless and until you do it in a controlled environment. That is a bit tricky with respect to laser texture. Okay, so that if you try to control it in a controlled environment, you can achieve a better result. But a repeatability point of view, obviously there will be here and there, because it has lots of other parameters which get influenced, like your heat transfer characteristics, etc. So those are things which we need to look into. Okay, so can we move to the next module? Okay.
Yes, sir. Yes.
Okay, so the next model which I am going to talk about is, it's a company project, it's an industry project So like a company which manufactures the engine blocks. So this is an engine block. Okay. So this engine block is basically made out of aluminum alloys. So basically it is made out of cast iron. But nowadays with the recent norms and everything, they would like to reduce the weight of these vehicles. So they are planning to go for these aluminum blocks. So basically they cast these engine aluminum blocks. But the major challenge in this is here you have a piston and a connector. So the piston will be moving inside these cylinders. So what happens is there will be a continuous amount of wear and tear happens in these cylinder. So how to avoid it? So the one option would be you need to do some kind of heat treatment in such a way that you create some kind of hardened layer over here. But the problem in this is, or I would say what we thought is, we have heard about this ALN, aluminum nitride. So this aluminum nitride is one of the hardest metals. So what we suggested to the company is, why can't we create some kind of aluminum nitride layer over here? Already your block is aluminum. So only thing I need to do diffuse some kind of nitrogen in this environment so that this block area becomes aluminum nitride, and then I can have an improved wear property. So with this as an idea we started. So but the major challenge in this is, again, I cannot heat this completely in a nitrogen environment. So we went for a technique called laser nitriding. So this will give you a better clarity, in fact. So this is your cylindrical bore and this is your can trace. So inside that cylindrical bore, I am just looking for some kind of laser nitriding combined with laser horn. So basically some kind of laser pattern. Like we all know that normally when a piston is moving inside the cylinder, so there is an oil, it should have oil retention capability. So what they will do is, they will have some kind of pockets over there. So inside these pockets, oil will be filled, so that when the cylinder moves up and down, it tries to get the oil from it, and basically it has a reduced in the friction. So here, now when I try to look into this process, I need to nitrate this layer as well as I need to create these pockets. So basically it is something like, I need to go for some kind of laser texturing or laser horning process. In the meantime, I need to do a nitriding layer on this. So with this as an idea, what we did is we went for this technique. So basically this is a simple laser material processing technique. So where you have a nitrogen gas which is being pulsed and you have a laser beam over here. When you irradiate this laser beam on this nitrogen gas, finally you end up in some kind of nitride layer on the surface. Okay, so we want to check this. And second thing is, already since we have the theory with us of overlapping, so when I try to do the overlapping, I can create a good amount of roughness pattern. And second thing is, I can also create some kind of uniformity in it. So with this as an idea, we approach this problem. So these are some of the research methodology which we employ. Basically, our laser has three different wavelengths, 355, 532 and 1064. Basically, we were looking into its fretting wear behavior of it, and we need to optimize the laser parameter, and we have to do some characterization of this. So we did a laser nitriding of these aluminum alloys using this Nd:YAG laser. So this is our experimental setup. So in this experimental setup, you have a pulsed Nd:YAG laser where you have a prism. Through this prism, laser beam is focusing. It is being focused on the sample, and here I'm just adjusting the standoff distance based on my arrangement. If you see this is my effective spot area, which would be helpful for me to study the area or the characteristics in this. So for purging the nitrogen, what I do is, currently this is a manual arrangement. Now we have made some kind of automated, which I have not included over here. So here I am just purging the nitrogen gas at a particular flow rate, and during the purging I am irradiating with the laser. So what happens is, so when the laser strikes the material, it gets heated up. When the laser strikes the material, it gets heated up. In the meantime, when you are just purging the nitrogen in this nitrogen will get diffused along the molten layer, and finally when it gets quenched, you get a hardened layer. So that is with that as a concept, we tried some experiments. So these are some of the overall process parameters which we employ. So basically we took two different wavelengths, 355 nanometer and 532 nanometer, and as usual, as I told that it's a frequency laser. So basically it's a 10 Hertz frequency and it's a 9 nanosecond pulse width. That means that 9 nanosecond means, since it's a 10 Hertz, for 1 second I will be getting 10 pulses. So if I try to take only one pulse of that particular second, the heating time for that single pulse is 9 nanosecond. Similar other times would be a cooling cycle. That is, 1 second means I take it as 0.1 second. In 0.1 second, 9 nanosecond is my heating time, and the remaining time is the quenching time. So 10 Hertz means in 1 minute I can go for a rapid tough on the material. And we did some fretting wear on the samples, whatever we have done some experiments in our laboratory, and this is the overall fretting wear test which we have employed, and we try to look into. So this is the fretting wear behavior with respect to the, because here wear is a major source. So basically I need to simulate the piston movement, so that I am just using this fretting wear experimental setup for my application. So whatever nitriding I have done, so I have checked the fretting wear behavior, and this is with respect to the untreated region with 355 nanometers. So this is your untreated region, and this is with respect to the different layers, where we found that not much variations were observed with 355 nanometer. Then we went for 532 nanometer, where there was a slightly better behavior, but at 1064 nanometer we got a better aspect. So basically this is something with 355 nanometer, not much variations were observed. So with respect to these variations, what we could observe is there was a huge amount of loss. Basically not much improvement in the samples were observed. Okay, so we went for a fundamental wavelength, that is at 1064 nanometer at 9 nanosecond. Almost we employed the same parameters. Only thing is we changed our laser fluence, like 510 millijoule per centimeter square, 1020 millijoule per centimeter square, 1530 millijoule per centimeter square, and with this we went for a different interaction with the material. So we found such kind of nitride layer over here, and this is your untreated zone. In fact, your nitride layer was getting improved with respect to increase in laser fluence, but once at 1532 nanometer we found some kind of distortions were happening. So we observed that 1020 millijoules per centimeter was a better thing, and this is your overall characteristic. If you see here, we are trying to reduce the texture pattern in this. So when we try to reduce the texture pattern, so we are just going for a continuous heat treatment, your continuous laser nitriding treatment in such a way that you can have a reduction in your surface roughness. So this GIXRD will give me a better clarity what is the whether my ALN phase is available or not. So you can see some kind of ALN phases are available over here, which is prominent with respect to 1530 millijoule per centimeter square and at 1020 millijoule per centimeter square, whereas in other cases it was less. So this is with untreated, this one. And even we did a fretting wear analysis, and with fretting wear analysis we could get a better result, because the wear rate was continuously coming down, and we could get a better mechanical property coming out of it. So this will give you a better clarity, because we have checked it with 2 Newton load, 4 Newton load, 6 Newton load and 8 Newton load, and we could get better prospects in this region. So this image will give you a better clarity on the laser nitriding which is happening on it. So this is the pin diameter of the untreated. When I try to impinge it, basically there is a removal of the material. At 510, at 1020 and 1530 millijoule per centimeter square, you leave such kind of traces over there. So this trace is something like, even after applying a heavy load, the removal is quite less. Okay, and these are some of the worn out surfaces which we have observed. Basically, we try to look into the different defects which is happening in, because since it's a industry oriented project, so we were more concerned about how the defect happens. So we were looking into this micro bits behavior, this oxide behavior and the wear depreciation. So my overall summary of this work is, basically we have attempted this laser nitriding technique. So in this laser nitriding technique, so what we have done is we have irradiated with a laser, we have purged the nitrogen in an environment. The major advantage of this is, since you have a cylindrical bore, you can manipulate the cylindrical bore, and wherever there is going to be an interaction of the cylinder piston, in that region alone we are going to do the laser nitriding, and combiningly we can do a texturing, which I am not reporting it over here, so that you can have oil retention capability in these engines. Second thing is, we have tried to optimize the parameter with a different wavelength and with the different laser fluence, where we observed that 355 and 532 not much, a good amount of improvement was observed, whereas with 1064 nanometer we had a very good improvement. The reason behind that is that 1064 nanometer you have a better optical absorption coefficient compared to a 355, and we could get a maximum hardness of around 2.07 GPa, which is quite good. In fact, some part of the cylinders we have already done it, and it has been given to the company for testing, and we are waiting for the results. So because of this COVID issue, we couldn't get the results. Somehow we are continuing this. So any doubts or any question in this module?
Any
No.
question from participant?
Regarding this laser nitriding?
No, sir.
Okay, so if that is the case, we will go to the next model, which we call it as laser forming. We all know what do you mean by forming. So metal forming concepts, basically it's kind of metal bending, buckling, etc. Okay, so there is a major drawback with respect to the conventional forming process. So that we all know that there is a spring back effect which comes into the picture. Second thing which I would like to explain about us, this is for my application. Basically, I work more towards this shape memory alloys. So in this shape memory alloys, basically when I try to apply a thing, and when I try to apply a heat, I can deform it. And when I try to apply a heat, it comes back to its origin. So this formability of this shape memory alloy is a challenging task. So what we thought is we need to go for some kind of other technique where we can employ a formability, because these kind of shape memory alloys are widely used for some kind of biocompatible as well as some kind of aerodynamic structures. So with this as an idea, we explored this region. So this is one good example. Basically, this laser forming is a very good technique. Basically, it has been employed in the year 1983. So this is mainly meant for thick plates as well as thin sheets also. So we have employed for thick plates as well as thin sheets. So if I try to closely observe it, this is an overall view or overall schematic of laser form, where you have a beam. You are just irradiating the beam on the sheet metal. So when we all know that when any material is getting localized heating, there will be an expansion and the contraction. When there is an expansion is there, you are trying to apply a constraint to it, so that what happens is during the contraction, the kind of thing. To give you a better clarity, I will just show you a taken which has been done at IIT Guwahati. So now you can see a video where we are just doing a small 2D laser forming technique. So this is a simple thin sheet which is being clamped, or basically I would say which is being constrained, and here you have a laser which is being irradiating on the surface. So when you try to irradiate the surface, there will be an expansion, and on cooling there will be a contraction. When there is a continuous expansion and contraction is there, so this will result in some kind of bending. So this is a simple 2D laser forming technique which is being employed. Okay, now let me just show you a video on 3D laser form. So this is, we are trying to create some kind of 3D structures. So you see a laser which is being irradiated over here. This is almost a kind of free sheet. Only at this region there is a kind of constraint which is being placed over here. So the main objective of this constraint is it doesn't allow you to move here and there. So you can see some kind of conical, some kind of corrugated structure you can get it. So this corrugated structure is basically taken care of the power which is being incident on it, and the constraint and the frequency of the laser or the interaction time of the laser over this region. So basically you can get any kind of corrugated structure coming out. So the main parameter in this is the laser energy, the laser interaction time, the constraint where I am applying, and how it is being employed for such kind of arrangement. You see a final shape, something like this. This is the final shape what you require. Basically this is for some kind of channel arrangement. Okay. So if I try to look into this mechanism, okay, so I think we are coming back to the slide. So if you try to look into this mechanism, basically this is my bend angle which I am trying to get it, and this is my sheet metal. I am just irradiating with a laser. So here my major parameter is my focusing optics, the sheet metal thickness, the interaction time, and the atmosphere what I am using, because that changes with respect to the different material what I am trying to bend it on it, and basically that will try to somehow convince my bend angle. Okay, so to understand the mechanism, basically there are three different mechanisms which is available in conventionally. One is bending, upsetting, and buckling. So the same mechanisms can be employed with the laser forming, so that you get a bending, you get a upsetting, and finally you get a buckling coming out of it. So as I have mentioned earlier, so basically this is something to play with the temperature gradient. So when the laser is being irradiated on this material, because of the variation in the temperature gradient, there is an opening and a closing, and because of this opening and closing, you get such kind of sheet metal bending, and this sheet metal bending will result in some kind of positive bend, or sometimes it results in some kind of counter bending, which is happening over here. So this positive bend can be something like this, or the counter bend can be something like this. So basically you have two different zones. One is a heat zone, which is a compressive stress. Another one is a compressive tensile zone, and the expansion in the compressive stress. So when you try to heat it in a localized region, so you can end up in some kind of expansion, and this expansion would be sufficient enough to create such kind of buckling or such kind of angle. Okay, so with this as an idea, let us take some of the case studies which are being employed in it. So one case study which we have did it for our laboratory. Basically, it's a company project which they requested, and then we have also explored the object. So most of you might be aware about this brake pedals and clutch pedals. Okay, like in your car. So we all know these brake pedals and clutch pedals are basically manufactured using a die punch, so for a mass production. But as far as an industry perspective, like which manufactured these brake pedals and clutch pedals, for each and every car or for each and every ergonomic design, you need to design this brake pedal and clutch pedal. So for this brake pedal and clutch pedal, so the major thing is you need to manufacture a die for these brake pedals and clutch pedal for different things. So like on a testing phase, I would say that on a initial R&D phase, for even for bending this layer, I need to design a die. So the die cost is quite high. We all know a die will be costing something around here to around 1.5. So, but if I need to change an angle, or if I need to test it, or if I need to do some kind of research and development activity related to an ergonomic design, I need to invest huge amount of money on the die. So what we thought is, we thought of going for this kind of laser forming technique. So what we went is, we went for a slightly high power laser, basically around 1.5 to 3 kilowatt carbon dioxide laser. And so these are the parameters which we have employed for it. So one is the passes, the energy, the scan speed, the laser spot dia, and the sheet thickness. So basically this sheet thickness is basically determined by the company, because the reason is based on this thickness they can change their clutch pedal and their brake. So here, by changing this parameter, so we could just achieve a different set of characteristics. So one of the major characteristics which we were trying to look into it is a bend angle. Basically in this project, we were supposed to make a software so that whatever angle you require, so you need to enter the angle, and you need to enter the thickness of the material, and you need to enter the type of the material. Whereas in this case, in most of these cases, the type of the material was same, so which the company was using. So when they try to enter into it, automatically it should give me laser parameters such as the speed, the interaction time, as well as the spot dia and the energy it is required. So we did lots of trials. In fact, we did trials with 3mm and 5mm, and we went on different characteristics like bend angle with respect to power, the bend angle with respect to scan speed, with the bend angle with respect to number of passes, and then we also went for a power bend angle. This is a better clarity which has been preliminary trials which you have done. So this is our heat affected zone, and this is the region where exactly the laser has been irradiated. Basically, this is a sample which is something around 10 mm. This is around 1 centimeter, because we would like to see the extreme value with respect to 1 centimeter. So what we did is we employed a 1 centimeter sample, and then we irradiated with a laser, and we tried to look into its behavior. And these are some of the microstructural analysis, as we all know. So these microstructural analysis will be helpful for me to study in depth, basically with respect to the unaffected region, with respect to the irradiated region, with respect to the same image, and with respect to the irradiated top region. So, and we also did some kind of tensile test in it. So what we did is we just tried to dice it along the laser formed region, and we made such kind of arrangement, basically EASTM EA, and we tried to look into the mechanical behavior of it with respect to the different power. Okay, so the reason behind this is, and this is our final product which we have manufactured, with a laser forming facility, and this is for a brake pedal, and this can be used for both brake pedal and a clutch pedal. Basically, this pedals are used in Mercedes cars. So those companies have the clients for these Mercedes cars for preparing this. In fact, they also appreciated the making up of this prototype. But the major challenge in this is, if you try to closely observe this mechanical property of the tensile test, if I try to look into its static behavior, there is a chance that it may end up in breakage, because there is a chance that, because this is your heat affected zone, under this heat affected zone, because of its detrimental effect, when you try to use it as an actual brake pedal or a clutch pedal, it may result in some kind of failure. Okay, so in order to avoid that, basically this mechanism was restricted only for prototype, and later it was so that they can reduce the cost of the die. They don't need to manufacture the die. So whatever prototype they want to make, that can be done using this technique. And with this prototype, finally, once their prototype gets cleared, they can go for a final product with a stamping for a large area. So that is what the idea behind this is a form. Now we have extended this work for some kind of microforming applications, because this can be employed for some kind of microforming application to create some kind of thin sheets, or to look into some kind of thin sheet behavior for different applications. Okay, so this is a copper foil which is used in some kind of bus bar applications, where we have formed using a laser microforming technique. So using this laser microforming technique, we could make such kind of copper foils which is being generated. So for that, there are different types of laser microforming techniques which are available. So one microforming technique which I would be discussing is a similar punch die mechanism, but the major thing is you need to completely observe the geometry, how the geometry works and how these micro features are being embedded into it. So what it is employed is, you have a die, you have a workpiece which is being kept over here, and this is your sapphire tool, and this is your laser beam which is being irradiated. Laser beam is made to irradiate it on the workpiece, and when your sapphire tool is being pressed, you get some kind of structure, something like that. So this is some kind of embossing which happens on the sapphire tool. So basically, you can create some kind of formability over this layer for some kind of micro channeling effect, etc. But the major drawback in this is, you have a sapphire tool, so there is a chance that you may need to replace the sapphire tool then and there, because of the load which you are applying. And the major advantage of going for the sapphire tool is, using the sapphire tool, your laser can easily be transparent and it can heat the material, and you can get any kind of complex shapes coming out of it. So this is one good example where an embossing is done using a sapphire tool, using a steam sheet, and where a laser is being employed for creating such kind of trench pattern on the surface. Next one which we are going to talk about is something related to laser shock form. So this laser shock forming is quite interesting, because some materials, when I try to induce a laser on it, there is a chance that it may have a detrimental effect, and it may have some kind of erosion or some kind of micromachining behavior. So to avoid that, so what we can do is, we can just employ such kind of laser where the laser is being focused just above the material. Finally, you end up in plasma. This plasma is made to push along the material, and when you try to push along the material, because of this plasma shock wave, you end up in such kind of structures. Okay, let me just show you a simple structure which has been created. Basically, this plasma will end up in some kind of gradient on the layer. So when it results in some kind of gradient, so basically it will induce some kind of residual stress on it. Because of this residual stress, there will be some kind of bending which happens, and this bending will be helpful for me to have a control over thin sheets. Okay, so this is a very good example where I have a silicon thin sheet which is being placed. By applying a shock wave of different levels, you can see the formability characteristics, because this is on a micron level forming. Okay, so by applying a shock wave over here, so this is what I achieved. There is an increase in the formability capability. Slightly moving its displacement, you can have a control over the displacement characteristics of it, or the formability bending ratio of it. Okay. The next one which we are talking about is something like, you might have heard about this die casting. Basically, it is something kind of pressure-based system where you have a laser, and the laser is made to incident on a sacrificial layer, which is basically on a black tape or something like that. So when the laser is made to irradiate it on these sacrificial layers, you will end up in such kind of plasma, and this plasma is expelled in such a way that you have a thin metal sheet. Finally, you can create such kind of buckle formation. Like for example, if I want to create such kind of lenslet arrangement, this kind of arrangement will be highly helpful for me to create such kind of buckled pattern. And these buckled pattern will have a capability for some kind of lenslet arrangement, or even sometimes if you want to use some kind of delicate layers. So these really delicate layers can be managed using this kind of laser radiation technique. So here you have a punch and tie mechanism, and you have here is the region where exactly a plasma formation happens. So with this plasma formation, there is a kind of a shock wave. With this shock wave, you can end up in such kind of patterns which is being exhibited over. Okay, so this is also an extension of this laser microforming. Basically, we were trying to create some kind of textured pattern on it by using a forming technique. So what we did is we went for a glass confinement, and with the arrangement of a thin film. So you just irradiate it with the laser, so that this will end up in some kind of plasma, and finally you end up in such kind of structures over there. So you can create any kind of pattern coming out of it. But obviously the features are limited, but still you can have a control over each and every features, and this is a low cost technique, so which would be helpful for us to create any kind of pattern structures on the surface. Okay, so overall summary of this module which I would like to explain is, basically we have looked into the concept of laser forming and the advantages of laser forming over the conventional forming. There some materials are restricted to conventional forming, which is being taken care by the laser forming technique. So we have also taken up an industry case study where we have used the laser forming technique for making brake pedals and clutch pedals for a practical application. Then we have also employed a technique for a micron level to create some kind of micro features. So for creating micro features, obviously directly irradiating the laser will have its own effect. So for that we have kept some kind of sacrificial layers in such a way that you create induce a plasma, and that plasma will be pushed towards a layer, and which we call it as a shock wave, and that shock wave will be pushed towards a layer, and finally you end up some kind of formability capability. So basically for a macro scale, what we thought of is something related to brake pedal and clutch pedal. For a micro scale, we were looking into some kind of lenslet. Okay, so is there any doubt in this module or any questions in this module? Or any queries or any comments?
Any questions from participants?
Sir, hi sir.
Yes, sir.
Is there any scope for laser forming? Like we can see what is the research in that laser forming? Sir?
Okay, see, actually, this laser forming now it is a booming area.
Okay.
In fact, I would say last 10 years back, there was a group working in IIT Guwahati, but somehow due to competition they left and they started focusing on theoretical. Now we have taken it up, and in fact, many industrial projects we are working with laser forming. So one example is this brake pedal and clutch pedal. One more example I will tell you, like this bus bar for this transformer. So this bus bar, basically they are made out of some kind of copper based alloys, and they are facing some difficulty with respect to this spring back effect in the conventional. So for those bus bars, currently we are also doing some kinds of consultancy work with laser form. In addition to this, the feature size what you get, okay, with respect to bus bar or any kind of channeling, so the feature size what you get with laser will be quite high. The precision of the laser forming which is being employed is quite heavy. So that is one good advantage of using laser forming. But the major drawback which I would like to say, in fact that I have explained in my slide also, see, you have a huge amount of heat effect. The thin delicate component you don't need to worry, whereas with the case of thick sheets, you have a heat affected zone. So this heat affected zone can be reduced by just purging some kind of gaseous environment, and you can, or sometimes using a water level, but that won't be much effect. So that is the reason normally we restrict it to some kind of prototype or some kind of static component. Like in the case of bus bar, we don't need to worry because it's a static component. But for a dynamic component, I still doubt that whether laser forming can be a promising technique or not. Like you cannot form a complete turbine blade using a laser forming. If you do that, obviously geometrical wise you can achieve it, but on the functionality wise, I doubt.
Okay, sir. Thank you, sir. Thank you so much.
Any other questions or any other queries?
Hello.
Yes, sir.
Sir, we can prepare the surface texturing by different methods. As you told, suggested laser surface texturing is one of the technique. Sir, if we will not compare with the conventional technique, then sir, what is the advantage of laser as compared to the average jet machine is there? One of the topic in this lecture in this webinar. After 2 days, one laser assisted ultrasonic milling. These are all the methods for the surface texturing. Sir, in what sense we can opt which method is suitable for the surface texturing? Which method will give best result?
Okay. See, actually, it basically depends upon your application. Like in my applications, whatever I have presented, it is more towards semiconductor industry. Okay. So if you try to look into the semiconductor industry, this abrasive based technique will have its own effect, right? Because semiconductor industry, we all know it's a clean room. So there, laser plays a major role. And second thing is, but laser has its own limitations, because one limitation which I told you is that it has a focus speed. So if I try to do it for a large scale production, it has its own deviation. So there is no, see, this is my understanding. Obviously, I might be wrong also. There is no particular technique which is 100% efficient for a particular application. Okay, it has its own drawback, but basically we try to optimize it in such a way that we use it for that application. Like one example which I have given with respect to laser forming of brake pedal and clutch pedal. Okay, see, laser forming of brake pedal can be, clutch pedal can be employed. But the thing is, obviously they have reduced the cost in because they don't need to go for a die. But when I try to look it into actual putting it on the bench, it is not possible. Because the reason is you have a heat affected zone over here. Like suppose in a simple term, I would say in a jovial term, if I would say I am just manufacturing a brake pedal made out of laser, and if you are on an emergency situation, if you just push your brake pedal, it may break at the interface. Okay, so but for that application of making a prototype, it has sufficed. Okay, so this is what my view. Like for it basically depends upon your application. You need to select your process. So if I am more concerned with the mass production, then obviously conventional has its own. Whereas for some kind of specialized or some kind of localized region, then this laser. Let me just give you one example. Probably slightly I might be debating it. You might have heard about this peening of gears. Gear at the root, basically you need to harden it. So normally people used to do is they used to put it in a furnace and they heat it. So along with the root, the entire area will get heated up. Whereas there is a concept called laser peening. In fact, some work which we are also doing, but which I have not recorded in this. When you use a laser peening, you can exactly focus on the root and you can harden. So that is one interesting aspects with this. So always all the process have its own pros and cons. We need to decide based on the application. That is my nutshell answer.
Sir, last question, sir.
Yes, sir.
Sir, suppose we have taken one steel sample and we produce different surface texturing over the sample with the help of laser as well as abrasive jet machine. Sir, in what sense we can discriminate the things? Because if we are producing the surface texturing over the surface, means some property will automatically enhance, like where properties have hydrophobicity, different property, obviously they will enhance the properties. But in what sense we can discriminate both the methods? Means property in laser also enhance, abrasive is also enhance. But
boss, why? But boss, my question is why we need to discriminate? See, the thing is, both the processes are good. Like you took a steel sheet. Now, where you are going to apply that steel sheet after texturing, where you want to use that steel sheet? Just a casual question. So I have a steel sheet. So you are just going to do a texture with abrasive as well as with laser. Okay. So now my question to you is, after texturing, where do you want to use the steel sheet? So if I want to use the steel sheet for some kind of rough work, like some kind of hardened area where open environment process, etc. For me, either I can use laser or I can use abrasive. Whereas if I going to texture the steel sheet and I'm going to use it for some kind of biomedical application or some kind of bacterial growth control, there laser is going to do. Okay, so that is what my nutshell answer is. It depends on your application. Okay, obviously your features might be different, but the thing is, basically it depends upon the application for which application you are going to select. So for some kind of sophisticated application, then I prefer laser because I don't want to take any risk. There are some kind of other applications where there is a huge amount of wear and tear going to take place. You can use a laser or you can use a abrasive also. But basically, frankly speaking, I'm not an expert in abrasive. I think Dr. Girish Verma from our lab only, our department only is going to give it up. He is an expert in abrasive. He will give a better clarity.
Okay, thank you.
Okay. So we won't discriminate any process. We will encourage all the process to what is there with us.
Okay, sir.
Hello, sir. Yes, sir.
Hello, sir.
Yes, sir. Any questions?
Hello. Sir, which material is more suitable for laser forming method?
Okay, actually, as per my experience, this is with my experience, I feel copper is good. Okay, and again, it depends upon the wavelength of the laser what you are using. So I have used a 1064 nanometer wavelength laser, a continuous laser, where I felt that forming a copper was quite easy. In fact, I felt that it was more interesting for me to make it into different shape. Even we made a small aerofoil from that copper, which we have given a prototype to GE for exploring some objects. Okay, so I feel copper was good. Copper was an interesting candidate, that is my experience.
Okay, thank you, sir. I am Gaurav. Thank you.
Yes. So, shall we go to the next module? Okay. So, I think I have given a brief overview about it. Now, I would like to give you some kind of input related to this underwater laser technique. Okay. Because this, most of you have asked me a question that why do we need to go for laser sometimes? See, the thing is, sometimes laser will have its own detrimental effect. So, one detrimental effect which I faced in my career, which then I addressed it using an underwater laser coating, which I would like to share it over. So one thing is, we all know about the shape memory alloy. So basically, the shape memory alloys, so it has its own behavior in such a way that, like when I try to crumble it, and when I try to heat it, it comes back to the original shape. Probably after this presentation, I will show you a video related to shape memory alloy and about our lab also. So those shape memory alloys, we want to do some kind of machining. So the idea behind that is, so I want to create some kind of micro channels. So when I try to actuate it, I can have a control over the flow rate towards these micro channels. So for that, when I try to do it in an open environment, it was changing its shape memory alloy behavior. So what I did is I went for a technique where I was just using a liquid. So this liquid is made to flow into it, and I have a shape memory alloy sheet. When I'm just irradiating with a laser, so obviously the amount of heat which is being transmitted on the material will be quite low, and because of that you get a proper channelizing. And second thing is, you won't have any detrimental effect on the energy. Okay, it will give you a better clarity. So this is on open air processing, where you have a laser beam which is being incident on it. You have a huge amount of debris which is being coming up. So when there is a debris which is coming up, there is a chance that because of again recast layer, so this debris may get deposited once again. Second thing is, when directly a laser beam is irradiating on the material, it gets heated up. When it gets heated up, basically it will result in some kind of change in the behavior of the material. And the second thing which I would like to see is, so this is on a running water condition where I have a beam which is being fed on it. So this beam, when there is a running water which is being placed, there is a kind of debris, and the debris is being washed out so that you get a proper properties, or what I would say is proper features what you require. Okay. Second thing is, I have my own selfishness because here I am using a shape memory alloy, so it won't hamper its property. Okay. So what we did is, we went on a process where we employed different characteristics such as material ablation and the number of pulses. So we did for an open air environment, and again, since I have a capability to go with different wavelengths, so I went for a 355, 532 and 1064 nanometer. And another one is, this is with an open air and this is with an underwater condition, where you could see with an underwater condition, because since there is a removal of the material which is happening, the energy which is being incident on the thing, it doesn't get wasted on the recast layer. So continuously your material ablation also will improve. So basically your machining characteristics will also improve. And this is one good example, or I would say that this is one comparison with respect to open air processing, and one example with respect to running water processing. So in open air processing, you can see this recast layer which is being available over here, and you have some kind of heat affected zone which is being available. Whereas in a running and processing, you get a smooth features what is required. Okay, so this is just to give you an understanding about the curve fit about the open air processing and the closed air processing. So for our application, we went for some kind of open air processing or closed air processing of the shape membrane structures, where we had a debris or we had a recast layer which is being built over here, and then we would just use a laser to create, and we closely observed that there were some crack formation and there were some recast layer which was being observed on it. And this is with respect to underwater processing, where your debris is completely free and you get a proper layer coming. Okay, so this is just to give you an understanding how an open air processing and an underwater processing plays a role. Okay, along with it, now when we go for a micron level, so here this would have given you an insight that when I am just irradiating with the laser, some kind of particle is coming out of it. So in an underwater processing, obviously there is a chances there when I am trying to flush out, I get a particle coming out of it. So the interesting concept in this is this, any plate if you take, let us take a copper plate, let us take a gold plate, let us take a silver plate, and a silver plate or a silver block, and I am just irradiating with the laser, there is a chance that I can just take out some of the particles coming out of it. Basically, it is on a nano size. Okay, so when I try to get it on a nano size, it is interesting for me because it has its own application towards cancer treatment, towards plasmonic effect, etc. So with this as a motivation, so what we did is we want to go for a nanoparticle generation. Basically, we were trying for some kind of plasmonic effect. So that is something kind of improving the solar cell capability or some of the functional application. But along with that, my major objective is I want to get a nanoparticle in an alloyed form. That is highly difficult because the reason is, like for example, think about a nanoparticle which is around 10 nanometer, which is in an alloy. So only option what you do is either you can go for a ball milling technique, where there also it is very difficult to get an alloy nature. So we took some alloy targets, something like some kind of nickel titanium, some kind of CuAl, etc. And we were more interested to get such kind of alloy layer. So what we did is we for different methodologies. One is we kept this kind of material in an underwater condition. We irradiated with a laser. When we are continuously irradiating with a laser, so what happens is this is a deionized water. We try to give some kind of disturbance always. So when there is a disturbance always, so what happens is the particle will try to come out of it and then you flush it and you take it. So this is a TEM image which will give you a better clarity. What is the size of the particle? It is almost something around 8 nanometer, a spherical particle which we have achieved with this technique. Okay, so we want to explore further. In fact, we did some kind of characteristics, basically some kind of BLS mechanism to study the nanoparticle characteristics in detail, and we also did some kind of XRD analysis to study the behavior, how whether really an alloyed formation is formed or not. So this is a clear clarity where you get an alloyed formation and a peak of an alloy formation which is being coming up. And the next methodology what we employed is we kept a target something like this. We had a glass slide. Over the glass slide we kept a droplet on it and we irradiated with the laser. So here we know that in our first mechanism itself we have studied that we have a vaporization, we have a melting, we have a vaporization, and we have a plasma formation. So the plasma formation is nothing but a pool of material which is being pushed to an environment. When it is being pushed to an environment, this particle will get dispersed, and I am trying to collect this particle in this underwater condition. Let me just correlate this with a natural phenomenon. You might have seen an asteroid or a meteor. So asteroid or a meteor, when it is away from the gravity, basically it will be just flowing. But when it enters into the gravity, it becomes a fireball. Basically, when it becomes a fireball, it tries to take a shape of a spear. Okay, so here also we require a spear. So what we did is we went for different combinations. One is we made a disc something like this and we irradiated with a laser, and when we try to rotate it, there is a continuous pull of the material which is being collected in the form of a water droplet. And then we try to look into it, DLS mechanism into it. And these are some of the simulation results. And the other technique what we employed is which we called as a grinding wheel principle. Like most of you might be using a grinding wheel. So in a grinding wheel is concerned, the grinding wheel when you rotate, when you try to grind your tool, the spark comes from the tool or from the grinding. That is an interesting thing. So when you try to collect the spark, you will be getting a material composition of both the tool as well as of the kind. So the same thing with this as an idea, what we did is we had a circular disc, something like this. So we used a water which is being splashing on this region. So we use a lens. So the lens was focusing on it. On a continuous rotation, there will be a splashing, and on splashing you collect it, and then on a sample container, and you try to collect these nanoparticles and you try to address it. So this is one of the TEM image. In fact, we went into the detail of the lattice behavior to see how these nanoparticles are being employed. And another configuration which we employed is you had a rotation base over here. So in this rotation base, when we try to rotate it, so there will be some kind of particle which will be coming out of it, and that particle will, because of the centrifugal force, it tries to come to the top surface of it, and then you can collect the particle which is being found. So these are some of the spherical particles which we have got in our system. Okay, so this is just to give you an overview. So basically, we use these allied particles for some kind of surface plasmonic effect. In fact, these allied particles has a very good application towards such kind of hydrogen fuel cells also, and which we are also exploring such kind of functions. Okay, so any doubts in this? Okay, or any questions would you like to ask related to this? So before ending this, I would like to just play a small video about my lab and what are the work what we are going for. Okay. So is this video visible? So some of the projects which we have developed in our laboratory. So these are some of the lasers which are available with us. So we have a continuous laser as well as a fiber laser as well as pulse laser. In addition to that, we also have many kind of thin film techniques which are available, like sputtering, E-beam evaporator, flash evaporation unit. So for characterizing, we have a temperature controlled tensile testing unit. We also have DSC analysis with us, and we have 3D printers basically for making some kind of optical kits. And this is one interesting thing, so which we have developed in our lab. So it's a metal 3D printer. Basically, we have it's indigenously made. Basically, we have developed this 3D printer in our laboratory. This is called as wire arc based 3D printers, where we manipulated a MIG gun to create such kind of any kind of features. So basically, even we have printed. This is mainly meant for shape memory alloy fabrication. Okay, so I can just show you a video where exactly we are using this. We have developed such kind of wire arc based dedicated for NITA shape memory alloy structures, so that you can feed the NITA shape memory alloy wire inside it, and you can create any kind of features coming out of it. And it has a capability to quench the sample at any time. So basically, we can feed argon gas into it and we can anneal it. And currently, we are upgrading the system with a kind of plate, a heated bed plate, so that heated bed plate would be helpful for heating up the system. Okay, so this is called as a shape memory alloy. So basically, this is a shape memory alloy because we have welded the shape memory alloy, which is highly challenging. So we have applied a weight to it. When you try to heat it, it lifts, and when I try to cut off the thing, it comes back. So this is the arrangement. So when you try to heat it, it gets lifted. So we were trying to look into its fatigue and life cycle behavior using this. So this is one shape memory alloy which we are actuating using a laser, and this is one laser forming technique which we have employed in our laboratory. So basically, this is a thin film shape memory alloy which we are trying to bend it using laser forming technique. It's a kind of crude trial version. So that even we have generated some kind of aerofoil structures coming out of it. So this is some kind of shape memory alloy based composite structure which we have developed in our lab. So basically, these kind of composite structures are being employed for some kind of aerodynamic behaviors. And this is a shape member alloy engine. Basically, it's a perpetual machine which is being employed for some kind of energy harvesting application. And this is a bimorph layer which we have developed in our lab. So this will be quite interesting. Basically, we are also working on some kind of underwater robot. So this is a underwater jellyfish which we have developed in our laboratory. So made out of shape memory alloys. So this is one of the project with MPO Kochi which we are working on. So for surveillance, etc. So this is one kind of fish kind of arrangement which we are developing. Okay. So with this, I would like to close my talk. So any doubts or any questions, I'm happy to address it. Or in case if you would like to write to me, you can note on my email ID. My email ID is palaniaa@iiti.ac.in. So I think I can type it over here. So so that it will be helpful for you. And I will just send my number also. In case if you want to contact me, you can contact me. So any doubts or any questions?
Sir, we have a question from the YouTube live chat by Raj Kumar. That how many scanning paths are required to produce the specific required angle in laser forming processes?
Okay, actually, that basically depends upon the material what you are selecting and the thickness of the sheet, how much you are doing. Okay, so that basically governs the number of laser passes.
Thank you, sir.
Any questions from participants? Okay. No one? Okay, then we conclude.
Hello.
Yes, any question?
Sir, I am Gaurav Kumar. This is very informative session. Sir, my question is at present, what is the application of shape memory alloy?
Okay, actually application of shape memory alloy and?
Yeah.
Application of shape memory alloy.
What is the future scope?
Okay. See, actually, shape memory alloy is concerned since it responds to heat. So basically, it is used for some kind of actuators applications. Apart from that, if I try to explore it, it has a wide scope. Even some of the ISRO has developed some kind of shape memory alloy based antennas, shape memory alloy based beams because of its true dielectric behavior. We are also working with some kind of shape memory alloy based. And we are also working on some kind of shape memory alloy based soft robotics, some kind of shape memory alloy based flappers, etc. Even once I gave a talk in SGSITS completely on shape memory alloy. So this shape memory alloy is it's a quite interesting area. In fact, India is now focusing more towards this area. A dedicated DRDO lab has been developed for these smart materials, where we are also a part of it. Okay, so as far as future prospects is concerned, see, last 5-6 years back, if you want to have a shape memory alloy, you need to rely on an international market. But currently, we have an in-house facility in India to manufacture these shape memory alloys. That was really good, basically. And in fact, future prospects with respect to Indian scenarios concerned, I would suggest that people should explore the possibility of manufacturing these shape memory alloys, because manufacturing in the sense that with respect to the material behavior. So you need to have a material manufacturing unit with respect to dedicated shape memory alloys, so that more research will come up in this particular.
Any one question from participants? Okay. Then thank you very much, sir.
Thank you,
Palani sir, who accepted our invitation to come over here for delivering your nice lecture. You deliver laser nitriding of aluminum alloy for improving its wear behavior. Combined study of annealing and texturing, flat top beam laser assisted annealing and texturing. Some experiment setup explained by you on laser texturing and underwater laser micro channeling and shape memory alloy. We are very, very thankful to you. Thank you, sir. Okay. So what over to you.
Okay. Thank you so much, sir, for this informative session. Our next session will start at 2:30 p.m. So please stay tuned. Also, please log in a few minutes prior to the afternoon session. Thank you very much.
feedback link has been sent to your WhatsApp group. Then kindly fill feedback.
Most probably the links will be same as the morning session. Okay. The Google Meet link is not going to be changed for whole FDP program, but YouTube streaming link may change. Whenever it may get changed, I will inform you accordingly. As of now, there will be no change for today's session. Both the links will be same. Okay.
Okay, sir.
So should we leave? हेलो नमस्कार हाँ किसके लिए मतलब ये रजिस्ट्रेशन तो क्लोज है ना रजिस्ट्रेशन ऑलरेडी कोर्स शुरू हो चुका अब कहाँ रजिस्ट्रेशन होगा नहीं 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 अभी नहीं हो पाएगा हाँ हाँ ठीक है अगर आपको सुनना ही है तो आप व्हाट्सएप ये इस नंबर से व्हाट्सएप ग्रुप में मैं आपको लिंक भेज दूंगा आप देखते रहिए उसको है ना ठीक है हाँ तो आपको थोड़ा सा पहले अलर्ट होना था ना इसलिए हाँ 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 ठीक है मैं इस नंबर पे आपको लिंक शेयर कर दूंगा ठीक है हाँ सुबोध को दे दिया ना, ठीक है, ठीक है, हाँ हाँ ठीक है। Okay, Subodh, can you hear me?
Yes, sir.
Okay, start.
Okay, sir. A very good afternoon to all our viewers. This session focuses on the topic of stability of rotor bearing system. We have with us Dr. Faisal Rahmani, sir. Sir, you received your PhD in Mechanical Engineering from Indian Institute of Technology, Delhi. You did your MTech in Engineering Mechanics from IIT Delhi in the year 2007 and Bachelor's of Technology in Mechanical Engineering from Aligarh Muslim University. You worked as a Deputy Manager R&D in ASME Telepower Limited, Gurgaon. You worked as Assistant Professor in Department of Mechanical Engineering, Galgotia's College of Engineering, Greater Noida. Presently, you are the Assistant Professor in the Department of Mechanical Engineering in Birla Institute of Technology, Mesra, Ranchi. You have several publications in international and national journals of repute and are an active reviewer of journals like Mechanism and Machine Theory, Industrial Lubrication and Tribology and Advances in Mechanical Engineering. Your research interests include journal bearings, vibrations, and rotordynamics. I welcome you, sir. Now, I would request you to please start with the session.
Thank you very much for such a nice introduction. Very good afternoon to all of you present here. Am I audible?
Yes, you are.
Am I audible?
Yes,
You are
sir.
audible, sir.
Yes, sir, audible.
Okay, thank you. So first of all, I would like to thank the organizers of this faculty development program at SGSITS Indore for giving me an opportunity to talk in this event today. So my topic of presentation is stability of rotor bearing system. As many of you must have basic background in mechanical vibrations, it will be beneficial to people who work in the area of dynamics and vibration in particular, and to all who are mechanical engineers in general. So I'll try to keep it simple so that you may understand the stability of a vibrating system or stability of rotor bearing system in particular. So we all study vibration of single degree of freedom system in our UG courses, but many of us don't study the stability behavior. So therefore, I'll first give some introduction about the basics of stability in case of a single degree of freedom system. Then slowly I'll explain to find the stability of more complicated system. So major portion of my presentation will be on the stability of rotor bearing system, specifically when the bearing is hydrodynamic type, because in hydrodynamic general bearings, stability is one of the main concerns. So let's get started. Let me just share my presentation. Okay. Is it visible to all?
Yes, sir.
Okay, thank you. So the topic of my presentation is stability of rotor bearing system. As you have introduced me that I am Faisal Rahmani and I am assistant professor in the Department of Mechanical Engineering, Birla Institute of Technology, Mesra. So first of all, what is stability? So general definition of stability is that if a system comes to its original equilibrium position after some disturbance, or if we displace a body from its equilibrium position, and if it comes to its original equilibrium position, then it is stable. So here is an example. So here there is a concave surface and there is a ball on this surface. So at this point, this ball is in equilibrium position. So if you just move this ball towards right, it will come again to its equilibrium position due to gravitational force. So this type of equilibrium is a stable equilibrium. So whenever you displace this ball from this equilibrium position, it will come to its equilibrium position. So in the second case, if the surface is convex and the ball is just at the top of the surface, so it is in equilibrium. But if you just disturb this ball from its equilibrium position, it will not come back here. So this type of system is unstable system. And there is one more type of system that is called neutral equilibrium. Suppose that ball is on a flat surface. So if you displace this ball from its equilibrium position, it will neither come to its original equilibrium position nor it goes far away from its original equilibrium position. So this type of equilibrium is known as neutral equilibrium. So in case of vibrating system, there are many type of instability. So I'll just talk here about instability of single degree of freedom system. So when a system is displaced from its equilibrium position, and as the time approaches infinity, if its position changes with time and comes finally to zero, then it is known as asymptotically stable system. So here is a graph showing the position as a function of time. As the time increases, its position is continuously coming towards the equilibrium position. Or in other words, you can say that the amplitude of vibration is decreasing continuously, so that finally it comes to rest at the equilibrium position. So this type of equilibrium is known as asymptotically stable system. Now in another case, when suppose the system is vibrating and with time its amplitude is continuously increasing, or we can say that its free vibration response grows without bound as time approaches infinity. So that type of system is unstable. So graphically here you can see that the position as a function of time, it is increasing, or its amplitude is increasing continuously. So as the time increases, its vibration amplitude goes on increasing. So this type of system is unstable. And there is a marginally stable system, it's normally the free vibration of undamped system. So in which free vibration response remains constant as time approaches infinity, or you can say that its amplitude doesn't change with time. So these are basically three different type of systems, and I'll just show an example to explain it further. Here is a system consisting of a bar which is vertical and hinged at this point O, and it is supported by two springs at point A. Now this is the equilibrium position. As long as this bar is vertical, it is in equilibrium, and these two springs are unstretched in this condition. But if we give a slight angular displacement theta to this bar, these two springs will deform. One will be stretched and another will be compressed. So due to its extension and compression, there will be forces generated in the spring, and that forces will try to push this point A towards left, and also this weight mg of this rod will shift slightly to the right, and that will give a moment about this point O. So in this condition, if you write the equation of motion by balancing the moment of all the forces about this point O, you will get this equation of motion. Now for small theta, suppose this theta angular displacement is very small, then we can approximate this equation by approximating sine theta equal to theta and cos theta equal to 1. So this equation simplifies into this equation. as I alpha, and the sign of alpha square will decide whether the system is stable. So if alpha square is positive, the system will be stable and this system will vibrate. And if the sign of alpha square is negative, the system, or even equal to 0, the system will be unstable. That means if you give a slight displacement theta, it will not come back to its original position, but this theta will increase continuously with time. So for the critical condition when alpha square is 0, this gives 4kl minus w is equals to 0. Thus, if 4kl is greater than w, the system will be stable. Or we can say that if the weight of this bar is less than some value equal to 4kl, the system will be stable. So if we see if the weight of this bar is less than 4kl, the system will be stable and it will exhibit vibration. And when the weight of the bar is equal to 4kl, just as on the critical position, it will become unstable and this theta will increase linearly with time. But if its weight is much more than 4kl, again it will be unstable and theta will increase, or the rate of increase will be more highest compared to this situation. And the rate, actually the theta versus time will be an exponential type of curve. So from this example, you can see that this simple system can be either stable or unstable depending upon the mass of this bar. So mathematically, we can derive some equation to know whether the system is stable or not. So let us consider just a simple system of a spring mass system with a damper. We all know its equation of motion will be given by mx double dot plus cx dot plus kx is equal to 0. So this equation comes from free body diagram of this mass. And if we assume a solution x is equals to e raised power st, so there is a reason to assume this type of solution because the derivative of exponential function is an exponential function, no matter how many times you derive it. So if you differentiate x as first time and second time, you will always get e raised power st multiplied with some other terms. So this type of solution can be assumed because if you substitute this equation into this equation, and this will be a solution only when if this satisfies this equation. So if you substitute this x is equal to e raised power st in this equation, you will get a characteristic equation ms square plus cs square plus k equal to 0. And there will be some other terms multiplied by this term, and that will not be equal to 0. Only this equation can be equal to 0. So from this equation, we will get two roots, and these are known as characteristic roots. And generally, it will be in the form of complex conjugates like p plus iq and p minus iq. So if we substitute this solution of the characteristic root and the final solution of this equation of motion will be c1 e raised power s1t plus c2 e raised power s2t. And if we again rearrange this by putting these two terms, we will get some amplitude multiplied by e raised power pt cos qt minus phi. So there are two unknown coefficients in this capital X and phi that can be found by initial conditions of displacement and velocity. But the important thing here is that this p, if we try to find out, this p will comes out equal to minus zeta omega n, where omega n is the natural frequency of the system, that is square root of k by n. And q is a measure of damping in the system, or actually this whole term is the damped natural frequency. So if we take the absolute of this root s1, that is square root of p square plus q square, that will comes out to be equal to the natural frequency of the system. And if you divide the real part of this root by natural frequency, you will get the damping factor. So we can see that if this term P is negative, then this whole response will be an exponentially decaying function. So the system will be stable in that case. But if this P is positive, then the whole response is an exponentially growing function. Then that system will be unstable. This is just a graphical representation of the how the nature of response when the value of P and Q is positive or negative. So this red axis is the original axis, and this is the origin. So if you see, this horizontal axis is the real part of S, and this vertical axis is the imaginary part of S. So when both the terms are zero, P and Q are zero, then the roots will be zero and there will be no displacement. So the system will be at rest. But if you have a negative part, so negative part of P, that means the real part is negative, then the system will be stable. But there will be no vibration. The displacement will decrease continuously with time, and finally it will come to the equilibrium position. And the distance of this real root from this vertical axis, like here the distance is more, it will give the rate of decrease. Like in this case, the rate of decrease will be more. Similarly, if the value of P is positive, the system will be unstable. But if the root consists of both real and imaginary part, like in this case, here both real and imaginary parts are there, but the real part is positive. So the system will be unstable and the vibration will continuously grow with time. But if there is no real part, only imaginary part, will get the just a vibration of undamped single degree of freedom system. So the main point in this graph is the distance from the vertical axis, or the more the value of P, the more rate of increase or decrease in the vibration amplitude will be there, and the more the value of this imaginary part, the more will be the frequency. Like from here to here, you can see that frequency here is more than this. But from stability point of view, just you have to see the real part of the roots, like P. Just you have to see the value of P. If P is negative, like all the portion here left to this vertical axis, in all these cases P is negative, so the response will be stable, or the response will be decreasing function of time. Finally the system will come to rest. So these all are stable system. So just by looking at the nature of the roots of the characteristic equation, we can say whether the system is stable or unstable. So this is for single degree of freedom system. Now, if we generalize this to multi-degree of freedom system, so the same equation of motion will be there, but it will take a matrix form. Here M, C, and K are mass, damping, and stiffness matrices, and these matrices are obtained by writing the equation of motion of all the individual masses and collecting them in a single equation. You will get this mass, damping, and stiffness matrices. Again, if you assume the solution of that exponential form, this equation will be reduced to this form, and for non-trivial solution, the determinant of this matrix ms squared plus cs plus k should be equal to 0. So if you find the determinant of this matrix, or it will be a characteristic polynomial in S, and the root of this characteristic polynomial are also known as eigenvalues. So characteristic roots and eigenvalues both are same in some sense. So we can find or we can know the nature of the system, whether it is stable or unstable, by just looking at the eigenvalues. So for a multi-degree of freedom system, These eigenvalues are generally complex conjugates, as we have seen in the single degree of freedom system, P plus IQ and P minus IQ. So in multi-degree of freedom system also, these eigenvalues are generally complex conjugates. So the sign of real part, which is important, the sign of real part indicates the stability of the system. So if the real part is negative, in case of multi-degree of freedom system, will get multiple eigenvalues. So for all the eigenvalues, if the real part is negative, then the system will be stable. And if there is a single eigenvalue whose real part is positive, then the whole system will be unstable. So for a stable system, all the real part of all the eigenvalues should be negative. So if the real part of all the eigenvalues are negative, the system will be asymptotically stable because the response will be an exponentially decaying function of time, as I explained earlier. So the threshold of instability will occur when the real part of roots becomes zero. So this is the case of like in the previous figure when the real part is zero and we get the vibration on the vertical axis. So we get the root on the vertical axis only. So this will be like a vibration of undamped system. So now coming to the rotor bearing system. So rotor bearing system is a way complex in nature than the simple single degree of freedom system and multi degree of freedom system because it is a continuous system and there are many things to consider in this rotor bearing system. So basically in a rotor bearing system there are two major components, that is rotor and bearing. Now this rotor can be rigid and flexible depending upon rotor is very short and diameter is large, then it can be considered as rigid, and if its length is long and diameter is short, it can be considered as flexible. Basically the differentiation between rigid and flexible is due to its stiffness characteristic. So if the rotor is very stiff, then it will come under the category of rigid rotor, and if it is not that stiff, it is flexible, then it comes under the category of flexible rotor. And the second part is bearing. Now this bearing may be of many types. Some of the types I have shown here, like rolling element bearings. There may be further classification in this rolling element bearings. There may be ball bearing, there may be roller bearing, and other types. And second classification is fluid film bearing. The rotor may be supported on fluid film bearings also. And this is the main topic of interest of my presentation, that is the rotor is supported on fluid film bearings. There may be other type of bearings like magnetic bearings also. So these are some applications of the rotor. Like here it is a gas turbine rotor, and it is from our BHEL Hyderabad. So you can see the size of the rotor. It's quite large as compared to our size. Again, this is a steam turbine rotor. It is also very large in size. So generally, large size rotor or very heavy rotors are supported on fluid film bearings like general bearings. So this is just a schematic of conventional general bearing. So general bearing consists of a bearing, also known as sleeve, and the rotor. This portion is known as journal, which is inside the bearing. This may be the rotor, uh, and there is a gap between the interfaces of journal and bearing, and in this gap lubricant is supplied through some convenient hole in the bearing. And when this rotor rotates, like here, when this rotor or journal rotates, it sucks the lubricant from the incoming hole and it drags the lubricant inside this. See, from geometry there is a wedge shape here. So lubricant is dragged inside this interface. Actually this is very much exaggerated. So the interface is actually very thin. So when this fluid is dragged inside this interface, a pressure is developed in this fluid film due to rotation of this shaft. Actually, the three things are responsible for this pressure generation. That is a converging wedge shape and the relative velocity between journal and bearing, and the viscosity of this flowing fluid of lubricant, you can say. So due to all these three conditions, there is a pressure generation in this lubricating film, and this pressure is responsible for supporting the weight of the rotor. So if we see the enlarged picture of this converging geometry here, so this flowing fluid will generate some drag on this journal surface and lift on this surface. So this lift will be responsible for supporting the weight of the rotor, and this drag will provide some friction to the lubricating film, and that will come as a part of energy dissipation. So coming to the bearing terminology, there are few terms defined in this figure. The distance of the journal center and the journal center OJ and the bearing center OB is known as eccentricity E. So in running condition, these two centers will be different. So the distance between these two centers is known as eccentricity. And the location of minimum thickness of the film is known as H min, or the minimum thickness of minimum film thickness. And here in this figure, theta, or the angle of angular from here, and when the system is in a stable condition, like the rotor journal is rotating at some particular speed and that speed is fixed, this journal will stabilize at some position OJ. And if you draw a line from OJ to OB, and the angle of this line with vertical load line is known as attitude angle. So these few terms are important that will be considered later. So from this figure, the film thickness equation is derived by this equation. Here the term C is the radial clearance, or the difference between the radius of bearing and journal, and this epsilon is a non-dimensional parameter given by the ratio of eccentricity and radial clearance. And another important equation in the analysis of this journal bearing is Reynolds equation, which is derived using the conservation of mass momentum equations. Like if you take a small element in the fluid film and apply the conservation of mass, we'll get the continuity equation, and if you apply the momentum equation, we'll get Navier-Stokes equation. And after simplifying various terms or neglecting higher order terms and combining both two equations, we'll get a single equation known as Reynolds equation. So this equation is very important because this is the only equation which can give you the pressure inside the film. This P is the pressure inside the film, and this H is the film thickness, mu is the viscosity of the fluid. So this equation is a partial differential equation, and this equation cannot be solved by any analytical methods. So only method to solve this equation is the numerical method, and generally we use finite difference methods to discretize this partial differential equation into a set of algebraic equation and solve that algebraic equation using some iterative methods. So basically the computational procedure will be like this. We divide the whole bearing surface into number of grids, and we know that on the boundary the pressure will be atmospheric, or if we supply the lubricant and at some pressure, so the pressure at the boundary will be the supply pressure. So we know the pressure at the boundary, and we divide the whole bearing surface into number of grids consisting of nodes. So if we know the pressure at this boundary where z is 0 and this boundary where theta is 0, we start by finding the pressure at this point and this point. Then in this manner successively we find the pressure at all the grid points iteratively, and then after finding this pressure we go to next iteration until some suitable error that can be acceptable is achieved. So like this value tends power -5 or -6, -7, depending upon the accuracy you want. You may solve this Reynolds equation using finite difference method. So this convergence criteria is nothing but it is a form of average pressure that we would like to achieve. So steps are, first you have to discretize the Reynolds equation using finite difference method, then solve the resulting algebraic equation using Gauss-Seidel iterative method. Then pressure is integrated over the bearing area to obtain the bearing force, friction force, coefficient of friction, and all further thing is obtained. So most important thing is to find the pressure. Once you find the pressure, you can obtain every other parameters. So stiffness and damping coefficients can also be found by finding the bearing forces. So these are the relation for bearing performance parameters. Like I said, if you find the pressure and if you integrate that pressure on the bearing surface, you'll get the bearing forces. So in this figure, I've taken two another axis, a capital X and capital Y. These are vertical axis and horizontal axis, and we can get the bearing force by these equations, and the resultant can be found by this relation, and this resultant will be equal to the load of the rotor or the weight of the rotor, that is the load which is supported by the bearing. These forces can also be found in another direction of radial and tangential direction by using these relations, and we can find the attitude angle phi by this relation. So first we have to find the forces in x and y direction, then convert this into r and t direction, then we can find phi or attitude angle by this relation. Now the fluid film can be assumed as a spring and dampers. Like if you apply some force on a fluid, it will resist. So there may be some stiffness or damping characteristics attached with it because this fluid is pressurized. So we simplify this system by assuming some stiffness coefficient and damping coefficient in horizontal and vertical directions. So here vertical direction is taken as capital X and horizontal direction is taken as capital Y. So in case of a fluid, there is some special type of stiffness and damping also, that is KXY and KYX, cross type of damping or stiffness. Because in fluid, if you apply a force in one direction, you will not get the resistance only in that direction, but in another direction also it will resist. Like suppose you are taking a ball and if you are pushing that ball in a bucket of water, the ball will not, if you leave the ball, it will not come directly above. It may be slightly displaced sideways. So that is because these two cross-coupled stiffness and damping comes into picture. So general definition of stiffness and damping is it is the rate of change of force in that direction. Like Kxx is del Fx by del x. Similarly, all the stiffness and damping coefficients. Actually, these stiffness and damping coefficients are linearized stiffness and damping coefficients. Like if you linearize this force by Taylor series and then find the stiffness, and if you neglect higher order terms, then you will get this equation. So in case of rotor supported on general bearings, so there is a perturbation method to find the stiffness and damping. Actually, previously the Reynolds equation was derived for a static condition, like this rotor is stable at its position at some constant speed. But in practical, there may be slight speed variation, and due to that speed variation, this position will change. The center of the rotor will change, and this film thickness will modify accordingly. So for a small change in this journal center, like here, suppose this OJ0 is the static journal position, and the position is slightly perturbed to OJ, that is final position, x0 plus delta x, y0 plus delta y. Then the film thickness equation will be changed, and initially, if you say take the angular coordinate from vertical axis, the film thickness equation will be CR plus, here CR is the radial clearance, and plus E cos theta minus phi, and if you further expand this and rearrange this, you'll get this equation. So perturbed film thickness will be something like this, steady state film thickness, or the film thickness in the static condition plus these two terms. Now, if you see the Reynolds equation, there are the last term del H by del T. That del H by del T comes into picture when this journal is in dynamic condition. So that del H by del T, if you differentiate this equation, you'll get this equation. So in the present work, a very small amount of delta x and delta y is taken for perturbation to find the stiffness and damping coefficients. So these stiffness and damping coefficients are found by using finite perturbation method. Like very small perturbation you give and you find the forces in the perturbed position, and just for a positive delta x and negative delta x, you find forces in x direction, and this derivative del fx by del x can be approximated by central difference method, and we can find the stiffness coefficient in x direction, that is kxx, by using this equation. So this is approximate method, but if you take this value of delta x very small, it will almost converge to the exact value. So similarly, a damping coefficient can also be found by perturbing the velocity, like positive velocity delta x dot and negative delta x dot, similarly in y direction also. So in this way we can find all the 8 dynamic coefficients of the general bearing, and it is important to find these stiffness and damping coefficients, because these coefficients will decide whether the system is stable or unstable. So first of all, let us consider a very simple system, that is stability of a rigid rotor. That is, this rotor is rigid and the whole mass of this rotor is twice m. So we can think that this total weight is divided equally on these two bearings, like mg here and mg here. And if we simply consider a mass m here, and that is attached by a spring and damper of these stiffnesses kxxs, kxy, kyx, kyy, and this type of dampings, and we write the equation of motion of that mass in the bearing, we will get two equations, and if we rearrange those two equations in the matrix form, we will get these equation of motions. So the general solution, as explained earlier, will be of complex conjugate type. So if we assume the solution by assuming a complex term, so this may be a general solution. For delta x and delta y is the displacement from its steady state position. So the threshold of instability will occur when this real part becomes 0. When this real part is negative, the system will be stable. So just at the threshold of instability, this gamma should be equal to 0. And if we equate this gamma equal to 0 and put this equation in this equation, we will get this equation. So for the non-trivial solution, the determinant of this matrix should be equal to 0. And by taking the determinant and separating the real and imaginary part, and further simplifying, we'll get a stability parameter defined by this equation, k equivalent divided by lambda critical square, where this lambda CR and k equivalent are dependent only on the stiffness and damping properties. Here, bar denotes the non-dimensionalization of this stiffness by this relation. So, if for a system we know the mass, speed, radial clearance, and its weight or the load on the rotor, then we can find the M critical, which is also known as the critical mass, and but I have used it as a stability parameter. So if this term by operating parameters or the system parameters, if you find, and this term comes less than the M critical find out by equations, then the system will be stable. So for the same system, here the dynamic coefficients like stiffness coefficients and damping coefficients are plotted with a modified Sommerfeld number. So modified Sommerfeld number is nothing but this equation, and it is a non-dimensional term obtained by almost all the operating parameters and geometrical parameters. Here ns is the speed in rotation per second. So you can say that higher Sommerfeld number is an indication of higher speed or lower weight or lower load, you can say. So just by assuming that the weight of the rotor is fixed, and if you increase the speed, this Sommerfeld number will increase. And the important thing to note here is that all these coefficient of stiffness and dampings are not constant with speed, are changing continuously with speed. So these all, in case of in simple system that we studied, in case of single degree of freedom system, we generally take constant stiffness, or we take spring which has a constant stiffness. But in case of fluid film bearing, these stiffnesses and damping terms are not constant with speed. So as the speed changes, the value of these constants or stiffness coefficients and damping coefficients will change. And after some speed, one of the stiffness coefficient like kyx, that is cross coupled stiffness, becomes negative. So when this cross coupled stiffness becomes negative, it will try to destabilize the system. So before this point, towards left of this point, or the speed less than this point, the system will be stable always, because all the coefficients are positive. But when this after some speed, when the stiffness coefficient kyx becomes negative, so it will provide a destabilizing effect on the system, and after some speed the system will become unstable. Damping coefficient also changes with time, with speed, and direct damping coefficient like Cxx and Cyy, these changes with speed, but the cross coupled damping coefficients, actually they almost remain constant with speed. So the higher the damping coefficient means that the amplitude of vibration will be lesser in higher speed. Actually, our system is very complex, and many things will depend upon the values of all these coefficients. So if we plot the stability parameter that we have derived earlier with Sommerfeld number, we can see that at some speed below this point, the system is highly stable. And after this point, if the speed increases, system stability parameter value is almost constant. And from the system parameters, if you find the value of mcr omega square by w, if that value comes below this line, then your system will be stable, and if it comes above this line, the system will be unstable. So this is the threshold curve for instability, you can say. Now, for the second case, suppose that the rotor is not rigid or the rotor is flexible. So the rotor itself will deform. So in this, again simplifying this flexible rotor case by assuming that this rotor shaft is massless and it has a central disc here which has some mass m. Then we can approximate this flexible shaft with some stiffness and we can neglect the mass. And these stiffness and damping terms are for the bearings. And for this whole system, if you write the equation of motion, like these two equation of motion are for this disc, and these two equation of motion are from this bearing. So here there are four displacement parameters: xy of the central disc and x0 y0 of the general center. So the system becomes a 4 degree of freedom system, and the general solution, we can rearrange these equation into matrix form also. But without matrix form also we can assume the general solution like this, and after putting this general solution in these equations, we'll get some equation in matrix form, and the determinant of this matrix or the coefficient matrix will give you characteristic equation, and the root of that equation will decide whether the system will be stable or not. But in case of fluid frame bearing, the only problematic thing is that with the speed, this stiffness and damping coefficient changes, and that will, as the speed increases, that will lead to more unstable state. And after some critical speed, the system becomes unstable and the vibration becomes out of bound. So mathematically, for a non-trivial solution, the determinant of this matrix C must be equal to 0, and the root of this characteristic equation will give you eigenvalues which are generally complex. I've said it earlier also. So for the stable system, the real part of all the eigenvalues must be negative. So for this system, for all the eigenvalues, I have just taken the maximum, the value of maximum eigenvalue and plotted it against the speed. So here you can see that this black curve is for rigid rotor and this red curve is for flexible rotor. So as the speed increases, this real part of eigenvalue, it is coming more towards the 0 value. So suppose we are considering rigid rotor. So from this point left to this point, the system will be stable because the real part of the eigenvalue is negative. But towards the right, it will be unstable because the real part of eigenvalue becomes positive. But the important thing to see here is that the flexible rotor is a little less stable than a rigid rotor. So in case of rigid rotor, the stability limit speed is high as compared to a flexible rotor. So this is the plot of the response. Suppose in the last figure, this is the stability limit speed. So just below this speed, if we obtain the response of the rotor by, suppose here is the steady state position, and hypothetically if we just displace this rotor to 0 position and leave it, it will vibrate or it will just follow a spiral path and come to this static equilibrium position or steady state equilibrium position. So just below the stability limit speed, the system is stable, and just after the stability limit speed, if you leave the system from 0 or origin, it will follow a outward spiral path, and its position from its center will continuously increase with time. So this figure shows the difference between a stable and unstable system. So for more complex systems, like maybe there are many disks on the rotor, like a real system of a steam turbine or gas turbine. There may be several blades row, and we can consider each blade row by a disc. And there may be this shaft could also be not massless. So for these type of complex systems, the method of analysis is generally finite element method. So in that method, we divide the whole system into number of elements and nodes. So for each element, there will be some stiffness matrix and mass matrix. And just giving an idea for a element of single element, like for this element, if you write, if you drive the stiffness and mass matrix of this single element, you will get this type of element. And finally, if we assemble all the elements together to form a single equation or single matrix equation, then we will get this type of relation. So, here in this equation, this M is the mass matrix, C is the damping matrix, omega G is a gyroscopic matrix. So I'm not going into detail of this gyroscopic matrix, but the point is that to highlight how a complex system can be dealt with. So this equation can be further simplified into by a state space formulation into two equations, and that two equations can be further written as ax dot plus bx is equals to 0. So this is the final simple equation, and we all know how to find the eigenvalues of this type of equation. So the eigenvalues of this type of equation will be same as the characteristic root of this equation. So just for illustration purpose, I have taken an example and find out the natural frequency versus rotor speed and damping factor versus rotor speed. So actually the absolute of the characteristic root, that is the square root of real part, square sum of the square of real part and imaginary part, and taking that square root, that will give you a natural frequency. And if you plot that natural frequency with speed, we see that natural frequency is changing with speed. So this is also a special thing about this type of rotor, that natural frequency changes with speed. And that is because the stiffness and damping are all also changing with speed. And the second thing is damping factor, that is it will come out to be the ratio of real part with natural frequency. So if damping factor becomes negative, that means the system will be unstable. So if I enlarge this much portion of this figure here, so we can see that after a speed of around 2000 rpm, the system is becoming unstable. So these are the methods to find the stability of more complex systems by using finite elements method. So now, after knowing what is stability and how to find the stability, so our main purpose is how to improve stability. So this is the question. So we came to know that in case of general bearings, the stability is a problem. So how to improve it? So there may be several types of methods to improve the stability. So basically the rotor bearing system consists of two things, rotor and bearing. So either modifying the rotor or modifying the bearing can change the stability of the system. But the modification in rotor is impractical due to many reasons, because cost, and also it will hamper the operation of the rotor. So we cannot actually modify the rotor. So only thing we are left with to modify the bearing. So there are many methods to modify the bearings also. So like alternative lubricants. So we can use alternative lubricants like I have taken powder, but other type of lubricants can also be taken. The main idea of the alternative lubricant is to change the coefficient, dynamic coefficients. So for different lubricant, that value will be different. Second type of change we can do is modifying the bearing geometry. Like we can take elliptical bore or multi-lobe bearing. So further, I will show some example on elliptical bore. And we can also provide surface texture or pocket on the inner bore surface of bearing. That also improves the stability, and that stability is improved by improving the pressure on in the lubricating film. So coming first to the alternative lubricants like powder. So powder lubricants actually are neither fluid nor solid, but in certain circumstances it can behave like a fluid. So when the particle size of powder is in the range of 1 micron to 10 micron, so experimental studies showed that some types of powders like molybdenum disulfide and tungsten disulfide behaves like a fluid in that range. So to find the mathematical equation for powders, actually it is very difficult to find the mathematical equation for real powders. So some assumptions are taken, like assuming that the powder particles are spherical in shape and the distance between consecutive particle is very less as compared to their diameter, and all grain particles are equal size, and its spin is neglected, and the effect of interstitial fluid. So these are very restrictive assumptions, uh, but it simplifies the mathematical equation drastically, so that we can find some results and see the nature. So pressure, viscosity, these terms can be found in case of powders by just simplifying or just considering the collision of two particles and simplify. Actually, these terms are obtained by considering these two molecules just like the molecules of a fluid. And one important thing plays an important role is this term V bar, that is the fluctuation speed of individual grain particle. Like when these grain particles are in motion, this will also vibrate about its mean position. So that will when two particles collide, that will exert pressure on each other, and consequently they will exert pressure on the walls. So these are all simple empirical relations, and in this constant T can be found only experimentally. So this is the problem with the formulation of powders. So we have to find the coefficients only experimentally. Similarly, viscosity and other terms can be found, and same method of governing equation like continuity equation, momentum equation, and energy equation can be applied to powder flow also. So, but in case of powder flow, these equations take a little bit of complex form and are difficult to solve. So further, many assumptions are applied. Although these are assumptions, but these are very realistic assumptions. So body force and inertia force are neglected. Pressure is assumed constant across the thickness of the lubricating film. Flow is laminar and neglecting higher order derivatives. So all the previous equation is obtained in this simple four equation. So now solving this equation, uh, first of all solving this energy equation to find this fluctuation speed V bar, and that V bar will be used to find the viscosity of the average viscosity of the powder film. So I'll just leave this mathematical part, but I have to say that the Reynolds equation obtained for powder lubrication in a similar manner that we obtain for oil lubrication. The Reynolds equation in case of powder is a little bit complex by involving more terms and by the derivative of pressure here, because in case of oil only del P by del X was there, but here 1 by P is also obtained here. So this puts some complexities in the solution of this powder lubricants, but this can be solved. And after solving these equations, we can see that here the figure shows the comparison between the stiffness coefficient of oil and powder. So we can see that this black line is for powder and this red line is for oil. So we can see here that the stiffness coefficient of powder is drastically changed. So stiffness coefficient of powder is much higher as compared to oil. Similarly, cross-coupled stiffness becomes negative at much higher speed. So we can say that the same rotor, if you support on powder lubricants, that will be more stable. But there are some other problems with powder lubrication also, like handling of powder and other things. So that are different matter. But stability can be improved by looking for alternative lubricants like powder. Similarly, damping coefficient is also drastically changed as compared to oil. And here also you see this curve is for oil and this is another curve for powder. So for powder, the stability limit for the same system, if only lubricant we changed when the stability limit speed was around 7,000. Now with powder, the stability limit is around 25,000 or 26,000 RPM. So there is a drastic change in stability on with rotors supported on powder lubricated general bearings. So this is one way to improve the stability. Another way is modification in the bearing geometry. Like here I have taken an elliptical bore. This circular bore of the bearing is slightly changed to elliptical bore. These are some terminologies for elliptical bore. So the main defining parameter of this elliptical bore is this value G, that is also known as non-circularity parameter. It modifies the film thickness, and this extra term comes because of this electricity parameter or non-circularity parameter. So in this case, by modifying the bearing geometry, by keeping the same lubricant, we are just modifying the film thickness. And due to modification in film thickness, the pressure will change and forces will change and everything will change. So the important thing to look here is, in case of an elliptical bore, there will be two converging and two diverging zone as compared with circular bearing. Like one converging zone will be here, and again here we'll get another converging zone. So there may be two pressure lobes. So these are some configuration of elliptical bore demonstrating the increasing value of G. If G is increased, the elasticity of the bearing will increase, and delta denotes the orientation of the elliptical bore. So both these G and delta will have some effect on the performance. Like for some elasticity, non-circularity parameter 0.5 and some eccentricity ratio 0.6. This eccentricity ratio will be defined by the operating parameters. So for different orientation, like when delta is 0 or 30 or 60 degree and so on, we will get pressure profile changed by the different orientation angle. So this bold black line is for circular bore, and others are for elliptical bore at different orientation. So here we can see that the pressure, maximum pressure in case of circular bore is high as compared to elliptical bore. So no doubt elliptical bore has some drawbacks, like the load it will support will be less as compared to circular bore. But in case of elliptical bore, if you see like this curve, so there is one pressure peak here, again pressure decreasing, and again there is another peak. Similarly for other configurations also. So for elliptical bore, there will be two pressure peaks. So if you say that a force is acting in one direction, then some another portion of the bearing, the force stabilizes that force. Or even in general term, you can say that the stabilizing force on the journal will be more as compared to circular bore. Now if we see the stability parameter with eccentricity ratio. So here in case I have shown the variation of stability parameter with eccentricity ratio. In the horizontal axis, Sommerfeld number is not there, eccentricity ratio is there. But eccentricity ratio is also dependent on speed. If all the parameters are fixed and speed is increased, this eccentricity ratio will decrease. It will have some like opposite effect of Sommerfeld number. So at high speed, eccentricity ratio will be low. But the orientation of the elliptical bore plays an important role in stability. So here on vertical axis, the stability parameter is divided by the stability parameter of circular bore. So if the value is greater than 1, then we can say that the stability of elliptical bore is more as compared to circular bore. So in major portion of this curve, the stability is more as compared to circular. The stability parameter is or this ratio is greater than 1. So in major portion of we can say that elliptical bore is more stable than circular bore. So the next modification we can do is by providing surface pockets. Like at entrance of the bearing, we can cut a pocket shape of maybe different shape like rectangular, elliptical, or whatever we want. But the main idea is that if you cut a shape, there will be a blockage of flow of lubricant due to this pocket. So when there is at the boundary, there will be a sudden jump in pressure. So that sudden jump in pressure will try to stabilize the system or modify the forces, and that will eventually lead to stabilizing the system. So these are the pressure profile for just for illustration. Like this pressure profile is for unpocketed or without pocket, and for the same condition, if we put a rectangular pocket in the bearing bore, see here at the when the pocket ends, there is a sudden jump in pressure. This is just the contour plot of this three-dimensional pressure plot. So this sudden jump will try to apply a force in the opposite direction just to stabilize the journal. Similarly, here on the bearing midplane, you can see the pressure profile. So by applying the pocket, the maximum value of this pressure is almost unchanged, but in some cases there are two pressure peaks, like here in this region and in this region. Just at when where the pressure is, sorry, pocket is ending, there is a peak in pressure. So that will try to stabilize the journal. So this figure is just on y-axis it is maximum real part of eigenvalue, and on x-axis it is rotor speed. And this curve, there are different curve for different pocket length. Like this black curve is for unpocketed bearing or bearing without pocket, and all the other curves are for pocket with varying length across the circumferential surface. So for not for all type of pocket length the stability will increase, but when the pocket length is substantially increased, or just the pocket ends after the you can say that converging zone and the diverging zone starts. So when the pocket ends in the divergent zone, there will be a pressure peak in that zone, and that will try to stabilize the system. So in case of surface pockets, we can see that the stability limit speed can be improved from almost 7,000 plus to 12,000 or 10,000 years. Just by modifying the geometry, we can also improve the stability of the system. So stability limit speed for different pocket shapes is shown here. So this is for without pocket. So this blue bar is for flexible rotor, and this green bar is for rigid rotor. So for all the cases of pockets like rectangular, trapezoidal, elliptical and parabolic, we can see that the stability limit speed is greater as compared to bearing without pocket. So by introducing pocket in the bearing bore, we can improve the stability. And in all the cases, the stability of rigid rotor is more as compared to flexible rotor. So coming to the end of my presentation, I want to conclude few things from my presentation, like rotors on hydrodynamic general bearings become unstable at high speeds, and stability of rigid rotor is more as compared to flexible rotors. Stability of rotors supported on powder lubricated general bearings is more as compared with oil lubricated general bearings. And stability can be improved by modifying the geometry of bearing, like using elliptical bore bearing, or stability can also be improved by providing surface pockets. So out of 4 type of pockets that I have analyzed, I found that rectangular pocket is the most beneficial for both stability and other performance parameters. So by this I conclude my presentation. These are some of the references. Thank you very much. And if you have any question, you may ask.
Any questions from participants?
Hi, Dr. Rahmani. Can I ask one question?
Yes.
Hi, I'm Sam from University of Warwick. Thanks for your presentation, and it was really nice and thoughtful of you that you started from the beginning of single degree of freedom system, then stability, and you have discussed all the things. I have one particular question.
Okay.
I wanted to ask one thing is you have towards the later part of the presentation while you were presenting some of the things which you have done in this area, you discussed about ellipticity of the journal, and just one vague thing which came to my mind is you were evaluating it for different ellipticity of journal, some parameter which you have chosen with which the major axis and the minor axis of the journal is kind of modified. But I just wanted to know that is there are people doing some kind of generic pressure profile, or to say a generic expression people are deriving for the pressure profile for some generic profile, because I can see one on one of your slides you give an expression for the pressure profile with the elliptic journal. But nowadays, with like people are measuring the journal profile directly from coordinate measuring machine, and suppose I have the coordinates x and y coordinates of the journal, then like if there's some generic formula or like taking a contour integral or something in that direction, something has been done, or it is only this kind of relations exist only for ellipticity, not for a generic shape.
Yeah, as far as I have presented, I have taken very specific elliptical bore just to mathematically model the things. But in case of real bearings, you can measure the actual shape of the bearing, and you can find the film thickness profile, and you just put as that film thickness profile to find out the pressure. So that can be done. So that will be more realistic. Yeah.
Okay, so you meant that the film thickness profile has been measured over the entire radial surface of the bearing.
Yeah. In my case, I have calculated it mathematically. But in real case, you can measure that film thickness profile, and you can put that film thickness profile in the program just to obtain the pressure profile. And in case of real bearing, also due to wear and all that thing, the shape of the bore doesn't necessarily is circular. It becomes elliptical or some other shape. So
that's what I was coming to. Yeah.
Yeah, that can be analyzed just by measuring measuring the film thickness profile, you can just put the new film thickness profile and you can find the pressure.
Yeah, but this film thickness profile will change with the speed of the journal inside the bearing. As the
Yeah.
speed will change, it will deflect to some different phi, and then the pressure profile will change across the surface. So then it has to be measured at all speeds.
So first you have after measuring the surface, you will have a base film thickness, and whatever film thickness is changing due to speed, that can be found analytically, and that can be superimposed with that film thickness.
Yeah, that is what might be the way to do it. Okay, that was the only thing. Thank you very much for your answer.
Any questions from participants?
Okay.
Anyone question from participants?
Sir, good afternoon, sir.
Good afternoon.
Can you hear my voice, sir? Can you hear my voice?
Yeah,
Yes, sir. Sir, in terms of packeting, rectangular packeting or elliptical packeting or a differential geometry in packeting, so what about the load distribution? Any impact on load distribution over the bearing?
Yeah, sure.
Yes, sir.
Load will also change.
So how it impacts, sir? How it impacts because of the geometry? You are removing the material support of the bearing shaft is going to be affected, no, because of the cavity. Sir. Packet.
No, actually we are providing the pocket on the bearing inner surface. That is, film thickness is always going to become higher. So in case of as compared to the circular bore. So, but providing pocket will just provide a restriction to the flow of lubricant, and due to that, pressure will increase in that region, and that will definitely going to change the load carrying capacity also. So, if the location of pocket is also important, if the length of the pocket is somewhere or the pocket ends somewhere in the diverging zone, then there will be a peak in pressure at the diverging zone also. So overall effect of the pressure, if you integrate over the entire surface, so overall effect will be to increase the load carrying capacity. But in other situation, when the length of the pocket is smaller, it will actually decrease the load carrying capacity. So by suitably choosing the length of the pocket, you can improve the load carrying capacity also.
Yes, so one more doubt, sir. That regarding the eccentricity of the shaft, which is mounted on the bearing, can accumulate the eccentricity in load conditions, huh? In shaft. Shaft eccentricity. The manufacturers producing the shaft with some permissible eccentricity. So how it's supposed to impact with the while running conditions with the eccentricity of the bearing?
See, in case of journal bearing, if the fluid inside the interface, like between the journal surface and the bearing surface, if there is a fluid and that fluid is pressurized, so in no way that journal is coming in contact with the bearing. So the problem is to maintain the film thickness. So in running condition, if there is sufficient velocity of the journal, the full fluid will be always sucked inside, and there will be a pressure generated in the fluid, and that will separate the surfaces of journal and bearing. So that will prevent from what is your concern, I think.
Because I think it may be in terms of ball bearings, maybe the influence. Maybe
Yeah, in ball bearing, both surfaces are in contact, but in case of journal bearing, those two surfaces
sorry, I may be wrongly understood that concept. Thank you, sir. Thank you, sir. Thank you.
Okay. Any questions from participants?
Sir, there is a question from Mr. Atul Modi.
Yes.
So the question is, like all heavy machines like turbines, compressors are using plain bearings, which have oil clearance. But in working, due to loading, this oil clearance increases in one side or load side, which affects the stability and bearing life both due to uneven film. How this problem can be minimized?
So in real conditions, the geometry of the bearing is modified due to wear, I think, and that modifies the film thickness. So that will give some deteriorating effect on stability. So, so to counter this problem, we can uh, actually geometry. If the bearing is installed, then it is not possible to change the geometry. So in that case, we can modify some by some means the lubricant properties. So actually stability can be modified by various things, like I said, by modifying the rotor properties or bearing properties. So in running condition, if we can't change these two properties, then we can change the properties of the lubricant. So by using different lubricant or providing some additives to the lubricant so that its viscosity is changed, and other parameter also depend on this viscosity, like when pressure develop will be changed and all the stiffness and damping coefficient will change, and that will improve some of the aspect of stability, I think.
Okay, thank you, sir. Any questions from participants? No, it has been asked on already. Okay, sir. So I
Just
conclude.
sorry, if
Yes.
there are no other questions, is there still time that I can slip in one more question?
No, you can ask. You can ask. Please ask.
Yeah. Dr. Rahmani, I wanted to ask one thing. A lot of people are nowadays working on MR fluids and all, especially in suspensions and other things. So I'm sure that there must be some investigations of people using magnetorological fluids in bearing instead of oil. Are there some things like this going on, or no? I'm wrong.
No, no, you are correct. There are research going on that area also. There are people are searching for many alternative lubricants, like MR fluid is one of them, and that also improves the stability parameters. So
Do you have got any kind of exposure in working in that area?
no, no, actually, I haven't worked in that area, but people are working in that area. That is also an open area, and people are rigorously working in that area also.
Mm-hmm. Nice.
Okay, sir. Thank you very much. So, thank you, Dr. Faisal Rahmani, sir, for accepting our invitation for this lecture on stability of rotor bearing system. Nice presentation. You nicely presented stability of a vibrating system, types of rotor, types of bearing, computational procedure, how to improve stability, use of powder lubricant, pressure profile, stability, and you concluded that stability can be improved by modifying the geometry of bearing. So, and you find that rectangular pockets will be beneficial. So, sir, thank you very much. And anything else from? So, Subodh, over to you.
Thank you.
Subodh,
Okay,
Subodh,
sir.
over to you.
Thank you so much, sir, for joining us. It was a very informative session for all. Our next session would be starting from 4:15, and the session would be on numerical predictions through in fluid and heat flow. Please stay tuned. Thank you.
Okay, thank you.
You're welcome, sir.
Feedback link, sir. Sorry for valuable class, sir. Feedback link.
Okay, feedback link we will send you. Feedback link we will send you.
Okay, thank you, sir.
हेलो,
हाँ जी सर।
क्या स्टार्ट करना है क्या?
सर अभी 1-2 मिनट और है सर।
है
1-2 मिनट और है सर।
हाँ,
4:15 का है सर।
2 मिनट।
हाँ 2
ठीक
मिनट
है,
है सर। ओके ठीक। ओके। सुबोध सुबोध
Yes,
हेलो
sir.
सुबोध
Yes, sir.
हाँ आर यू देयर?
Yes, sir.
हाँ ओके ओके ओके। Yes, you can start, Subodh. Okay.
Okay, sir. A very good evening to everyone. We shall now start with today's third session. But before that, I request you all to please ask questions by writing them in the chat box for the completion of presentation in the scheduled time. The topic of our session is numerical techniques for prediction of heat transfer and fluid flow. I would like to welcome Mr. Vinod Parashar, sir. Sir, you are a faculty in the Mechanical Engineering Department of SGSITS Indore and an alumnus of IIT Kharagpur. You have also worked as a design engineer in Volvo Eicher Commercial Vehicles Limited. I would now request you to please start with the presentation.
Okay, thank you. Shall we start?
Yes, sir. Yes, sir.
Just a minute.
Okay, sir.
Is it visible?
Sir,
My screen is visible?
sir, not right now. Professor Gani, please. Okay.
Just a minute. No, I have is it coming? Not yet. Just a minute. Present now. Okay. Then I should go to window, na? A window.
Yes. Yes, go to a window.
Then
and
share.
Go to your presentation.
Presentation or share?
No. Just to click on your presentation and that share.
First, I have to press share and then the presentation, na?
No. First, go to your presentation. Click on your presentation box and then share
Okay.
it.
Just a minute, array. It is it is opening in some other ID. So I have to change the ID for a minute.
No, no problem, sir. Take your time.
Okay. I will press share. Okay. Is it appearing now?
No, sir, it is not appearing. Professor Gani, it is appearing. Okay, sir. Go to present now box.
Yes, I have gone to present now.
Click on a window.
A window, okay.
And click on your presentation. in the box. There are number of files. It may be.
Acha. Okay.
And click on that your presentation, and that then share it.
I have clicked the presentation. Now I should share it.
Yes, yes. Your presentation is visible to you. That file is visible to you.
Just a minute. Just a minute. That file is visible to me.
Okay, then click on that file.
I have to click on
that file and share it.
File and share it. Okay.
Yeah. You can share it.
OneDrive.
No. Only share it.
I have pressed the share PowerPoint presentation.
Okay, share it. Then it will appear on the screen.
Just a minute. Should I call someone? Now it is coming, na?
Professor Ganni will tell you.
Now it is coming, it seems.
Okay.
Is it coming now?
Yes, it is coming. Yes, it is coming.
Okay.
Sir.
Fine.
And then now you can click on present one.
It is running slightly.
Visible to everyone.
Already I have pressed F5. I think
okay,
now
very nice. It is clear, sir.
Acha, good afternoon, everyone.
Yes, sir. Good afternoon.
I think now it is visible, na? I can start.
Yes, sir. Yes.
So the title of the presentation today is slightly I have changed the title. It is Introduction to Discretization of Heat Transfer and Fluid Flow. The title that has been mentioned is numerical processes in the heat transfer and fluid flow. I have slightly changed it to discretization. So in this discussion, we would be discussing briefly on the numerical techniques that are involved in predicting the heat transfer and the fluid flow processes. Now, already lots of softwares are being used by the engineers in the analysis, in the fluid flow analysis, in the thermal analysis, and in the designing of various equipments. So we'll try to understand what goes inside these softwares which are being used by the engineers commercially or in the academic field, how these softwares are modeled or how they are being programmed. Generally, in the fluid flow softwares, finite volume methods are more commonly used. And our stress would be more on understanding the finite volume methods. At the end of the lecture, we'll try to discretize one heat transfer equation in one dimension. And we will try to understand the concepts of discretizing the differential equations which are used. So as you can see, some of the important applications like the power generators. These involves the combustion of fuel and heat exchange between two fluids which are running at different temperature. All the operation of the power plants, it works on the fluid flow and the heat exchange. Air conditioning is another application. We need to study how the air is coming inside the room, cooler air is coming inside the room. What is the flow pattern, in which direction it is going, and how it is then cooling the objects. What is going to be the flow velocity? We can see whether it is going inside the corners, what is going to be the flow direction. Vehicle aerodynamics. This is another aspect which affects the drive stability at high speeds. It also affects the air drag. Flow separation is one of the phenomena which needs to be minimized in the aerodynamics through proper design of vehicle body. As we can see, aircrafts and jets, these would employ the heat transfer and the fluid flow to get effective lift, then to minimize the air drag, to get flight stability, and to reduce the propulsive power. Even the size of electronic circuits, that is limited by the effective cooling that we can provide. So the convective mechanisms of heat transfer are being studied in the circuit designing. So these are some of the important engineering processes in which we have to study the heat transfer and the fluid flow processes. Now, what are the outcomes from these softwares? What are the outcomes that people try to study from these types of predictions? So as we can see, temperature is one of the outcomes. In a flow field, it can be in a flame. We can study how the temperature is varying in a flame, how it is varying on a solid surface. These are some of the things. So temperature is one of the variables that is an output of these types of prediction. Pressure and velocity. Pressure variation inside a chamber, or it can be a pipe, or it can be a surface. How the pressure varies in a flow process. What are going to be the flow trajectories? These types of studies. So pressure and velocity are another type of outputs. Then you can also study the concentration of species if it is some chemical reacting chamber. All these types of studies can provide you the Nusselt number, the Reynolds number, the heat transfer coefficient, and the coefficient of friction. These variables can then be used to study the heat transfer, shear stresses, and the mass flow rates. If you, as an engineer, we will try to see how these parameters are affected by the change in geometry, or by changing the property of the fluid, or by changing the flow rates. So we can give some inputs as some variable parameters, and in return we can expect some outputs in the form of temperature, pressure, velocity, or the species concentrations. Okay. Now, most of you must have seen these grid type of structures, always visible on your platforms that you are using. Different commercial platforms are available, and people make 3D models on which these grids are many times visible. These can be cubical types, or it can be in some different shapes. As you can see, there are some grid visible on the surface of a pipe. These grids can be uniform in spacing. It can be non-uniform. It can be rectangular, triangular. Different types of grid shapes are. What are these grids? So if we see, some projectile type of shape is visible on which some rectangular grids are there. It appears that this projectile is flowing in the air. So outside the boundary of this projectile, there is another pattern of grids are visible. We will try to see what are these grids, why it is being made in these types of softwares. So let us come to a two-dimensional domain. As we can see in this figure, a two-dimensional domain is visible. Again, on this domain, there are certain grids, rectangular in shape. And at the crossing of these grids are some points called as the discrete points. We can call as the grid points also. Let us timing consider that this is some surface of a plate on which some heat exchange is going on. Heat transfer is taking place on the solid surface. This domain is bounded by the boundaries on all the sides, and different conditions are existing at the surfaces, which are called as the boundary conditions. Different boundary conditions can exist, like the surface can be insulated, it can be heated by a constant flux, or there can be a constant temperature existing at the surface. Different boundary conditions can exist, and we have to obtain the solution at these grid points. So for obtaining the solution, we'll be solving certain algebraic equations at the discrete points. So the solution is going to be discrete solution. That is why we call it as a discretization techniques. Although the solution would be discrete, means it will be at different locations, but there is going to be some correlation existing between the intermediate point. From one point to another, there is going to be some predefined condition prior existing. So it is, you cannot say it is totally discretized, partially discretized. As we can see, an experimental prototype or setup for solving the same problem, it will involve time as well as money. Then we cannot make too many prototypes. We would be in a position to make limited prototypes, and we may not be able to apply too many conditions also, boundary conditions also on that prototype. So compared to an experimental setup, these numerical solutions are more cheaper. So these simulations can be made much faster, and even you can simulate the ideal conditions. In the laboratory, you may not be able to always provide the ideal conditions. However, in the softwares, you can very well maintain the idealistic boundary conditions. Then even realistic conditions can also be simulated to a certain extent with certain simplification. Not necessarily total realistic predictions are possible, but to a greater extent, by certain simplification, we may be able to provide the realistic outputs. Apart from that, the solution that we obtain provides us the complete information of the domain, which may not be possible in an experimental setup. Like in an experimental setup, there would be certain locations which are inaccessible. You cannot put a probe. You may not be able to get the reading for those points. However, in a software, a complete information is always possible. So these are certain advantages. That is why people go for more and more in the numerical predictions before designing the prototypes. So, okay. So how these models are made? How these discretization techniques? So there has to be certain governing equations behind these. What are those governing equations? Now this figure shows a control volume on the screen. This control volume is having certain dimensions in the dx, dy, and dz. It is having 3 dimensions. This control volume is bounded by 6 surfaces on all the 6 sides. A very small control volume, infinitesimal small control volume, within which the flux would enter from the surface, and it would go out from the, it would enter also as well as go out also. Flux, by flux we mean it can be a flow flux, simply a mass flow rate. So that would carry some momentum along with it. By flux we can mean the heat transfer rate, watt per meter square. or there can be the flow of some chemical species inside the control volume, and it can go outside. So as you can see, in the x direction, flux is having a directional property. So it can, based on the coordinate system that we employ, the flux also has certain direction in which it is flowing, perpendicular to the surface area. So as you can see in the figure, flux Jx is entering in the x direction. There is E flux, that is the outgoing of the flux from the opposite phase, which is equal to Jx plus d by dx of Jx times dx. It leaves the opposite phase. So the net efflux in the x direction would be equal to flux out minus flux in, which becomes equals to d by dx of Jx. Similarly, the flux would be going in the y direction as well in the z direction. Summing up the total flux in all the three directions, we can write down the expression as shown on the screen. Net efflux would be given by d by dx of Jx plus d by dy of Jy plus d by dz of Jz. This is going to be the net efflux, which can be written in a single term as divergence of J. This divergence of J is a simplified way of writing the differential form in the three directions. So now this flux can enter in many ways. It can either get accumulated inside the control volume with time. There can be buildup of mass inside the control volume, or there can be buildup of species inside the control volume, or there can be buildup of energy inside the control volume. To such a term, as we see the governing equation for concentration of species, the first term is d by dt, which represents the buildup of the flux that is going inside the control volume against time. Here ml represents the concentration of species, u is the velocity, flow velocity, and rho is the density. So the first term would indicate the buildup of the flux against time inside the control volume. That is second term. The second term, divergence rho u ml, would indicate the flux that is going inside and coming outside by convection, by the flow process. As the flow is taking place, the species would go inside, come outside, or the heat would go inside, come outside, or the mass would go inside and come outside. Momentum can go inside. So this is the flux transfer by convection. There is a third term. So tau represents the diffusion coefficient. This third term would represent the diffusion of the species inside the control volume, and so on. There is a fourth term, which is a source, which is also called as the source term, or this would represent generation of the species inside the control volume. There can be certain chemical process taking place. You can expect certain particular species to be formed, or there can be a nuclear reactor in which per unit volume there is going to be some liberation of the energy, or there can be some source of mass within the control volume which is providing additional masses. So this is a source term. So we have seen the equation, governing differential equation for conservation of species. We can write down a similar equation for the conservation of energy, which is also called as the energy equation. So what you see on the screen right now is the governing equation for the conservation of energy for a steady state flow. In this, the first term is missing. As you see, in the first equation, there was d by dt term that we have neglected. In this, we are calling it as a steady flow. Although it would exist also, we can include very well inside this. So there are three terms in this energy equation. The first term on the left hand side is divergence rho u h. H is the specific enthalpy. Again, rho is the density, u is the velocity. First term would indicate the flow of energy by the convection inside the control volume. We had been discussing this control volume, this small control volume. So the first term is indicating the energy that is going inside the control volume by convection. The second term, divergence k grad T. T is the temperature. This term is indicating the energy transfer by conduction. And third term represents the volumetric heat generation within the control volume. So this is again a governing differential equation for the energy balance. There was one more governing equation for the conservation of species. There will be another governing equation, differential equation for conservation of momentum. Since we are considering the Cartesian coordinate, now this equation on the screen represents the conservation of momentum in the x direction. You also know it in the form of Navier-Stokes equation. This equation would be written for the momentum in the x direction. There will be another equation for the y direction and for the, right now you see one of those three equations. Again, the time variable term is visible in this d by dt of rho u. Then transfer of second term divergence rho u represents the transfer of momentum by convection or by the flow. That is third term, in which mu represents the viscosity, u is the velocity. So divergence mu grad u. This would represent the force generated by the viscosity, which we can also call as the momentum transfer by diffusion, similar to the conduction process or by the diffusion. Then there are three terms on the right hand side, which can be clubbed together to be called as the source term, dp by dx. Into the body forces, bx would represent the body forces, like the gravity forces if we consider in the y direction. And then vx term, which is the additional viscous terms, which we may account for some certain cases like turbulent cases. These additional terms can be represented in a constant form. So as you see, we have seen three governing differential equations which were made about this control volume. These governing differential equations defines the flow process or the energy transfer or the transfer or a chemical reaction to take place. All these three equations, they would be simultaneously satisfying the continuity equation or the mass balance equation. All these equations are supposed to satisfy the mass balance, which is also called as the continuity equation. What you see on the screen is the continuity equation or the mass balance equation. All these three equations can be written on a common platform. We need not to write these three equations differently. We can straight away write them with a single equation. We have replaced phi with temperature for the energy equation, or phi with the concentration for the species conservation equation, or phi with u, the velocity, for the momentum equation. So first term indicates the time variable term, second is the convective term of variation of convective transfer of the flux inside the surfaces. Fourth term indicates the diffusive transfer of variable phi inside the control volume, and S is the source term. So as you can see, all these terms can be written on a common platform. And if we can arrive at solution of any one of the equation, we can say we can have a similar solution for the other equations also. If we are in a position to solve either of the one of the equations, so we may expect a similar outcome for the other equations also. Okay. What are going to be the outcomes? as we have discussed earlier, the outcomes are going to be the temperature, pressure, velocity, or the species concentration, which we are writing as phi on the screen. This phi is function of the space coordinates x, y, z, as well as the time coordinate. So this phi would be varying all along the domain. It would also vary against time also. This phi would be a dependent variable. It would be dependent on the independent variables x, y, z, and the time. This phi can vary in 1 dimension, or in 2 dimension, or in 3 dimension, based on the type of model that we are developing. We can consider these equations to be in 1 dimension, or 2 dimension, or in the 3 dimensions, based on the simplicity or the time of computation involved. If we eliminate t out of this, if phi is not a function of time, then we would be getting the solution called as the steady state solution. Otherwise, the solution would be unsteady state solution. Okay. So far we have the differential equations. So far we have discussed about the differential equations. We want the solution from these equations on a discrete pattern, on a discrete points or the grid points. So if there are n discrete points in this domain, so then there are going to be n different values of phi. Suppose there are 10 points on this domain, so you'll have to find out 10 different values of the temperature, or 10 different values of the velocity, or the species concentration on all these points. So you need to have 10 different algebraic equations. When these algebraic equations are solved simultaneously, so you can say you are having a value of phi, which is a function of the space coordinates. Then for next time domain, you can have another value of phi as a function of space coordinates, and so on. From where to get these algebraic equations? So these algebraic equations we are going to obtain from the governing differential equations. We have so far discussed the momentum equation, energy conservation of species equation, the energy equation, momentum equations. These are the differential equations which would be converted into algebraic form. And then we will solve these algebraic equations simultaneously to obtain the solution of phi. Now, let us see. So on the grid, there are 3 points visible. We are considering a single dimensional domain. Means value of phi is varying only in one direction. Its variation in y and z direction are being neglected. There are point 1, 2, and 3. By Taylor series expansion, we can write down the value of phi in terms of the value of phi 2. Then the first order differential d phi by dx at point 2. The second in terms of the second order differential d square phi by dx square, plus the higher order terms, and so on. So value of phi 1 can be represented as a function of phi 2 in terms of the differential terms. If we can neglect higher order terms, there is going to be certain error in estimation of value of phi, or you can say there is going to be certain residue left in estimating the correct value of phi in the form of phi 2. That depends on the accuracy of the solution that we desire. Let us see value of phi 3. Phi 3 can also be written as a function of phi 2. Phi 3 can be written as phi 2 plus delta x by factorial 1 times d phi by dx plus delta x square upon 2 factorial times d square phi by dx square, plus so on higher order terms. So you have two equations, A and B. You remove equation A from B. You subtract equation B from A from B. B minus A. And neglect the higher order terms. So you can say d phi by dx first order differential at state point 2 is equal to phi 3 minus phi 1 upon 2 times delta x. As you can see, we have converted the first order differential into finite difference form. It is now a function of the values at 2 points which are separated by finite distance apart. Similarly, adding the equation a and b, we can get d square phi by dx square again at the point 2, which is again the function of phi 3 plus phi 1 minus 2 times phi 2 divided by delta x square. Again, we have obtained the second order solution in terms of the value of phi at the neighboring points. D square phi by dx square in a finite difference form we have obtained, which we can now very well substitute inside the governing differential equations. Those governing differential equations consists of the first order differentials and the second order. So we have obtained these values in a finite difference form. Let us go a step further. Let us focus our attention to a one-dimensional heat conduction equation. We are considering the heat conduction in a solid surface now. Now there is no convection involved. There is a solid surface, and only the heat transfer is taking place by conduction. So there are only going to be two terms in this. There is no convective term, there is no time varying term, only a conduct d by dx of k times dt by dx plus a source term is equal to 0. This is the governing differential equation. We want to determine the value of temperature, which is our variable, at point P. On the screen, again, there are 3 points visible. There is point P of our interest. We want the red point. This point P is having a neighboring point to the east, which is called as point E. This point P is having another point towards the west, which is called as point W. In between the 2 points, 2 grid points, there is one face, which is called as E face, east face, as shown by the dot. Similarly, between point P and W, there's another face called as the west face, W face. The distance between east and the west face is delta x, as shown in the figure. The finite volume, which is being shown on this figure, this finite volume has dimension delta x in the x direction, and its dimensions in the y and z direction are unity. It has dimensions 1, 1 in the y and z direction. What we are going to do is we integrate this governing differential equation over this control volume. Within this control volume, the volume that is bounded by the east face and the west face. When you integrate this, second would indicate the flux that is coming in from the west face by conduction inside this solid. Okay. Let us go ahead. Let us try to assume certain temperature profile between the point P and E. Now what this figure shows equal to sigma temperature of the neighboring nodes times their coefficient plus a constant. N represents the neighboring nodes. So temperature of our point P would be in terms of the temperature of the neighboring nodes. So now, so far what we have done is we have integrated the differential equations, and then the first order differentials and second order differentials are being substituted in the finite difference form, and differential equations now we can see are now in the algebra for different nodes. The source term also in this S. The source term is not independent. It is function of some constant term plus a function of the present temperature. So it can form also S is equal to SC plus SP dt. So our governing equation now varies slightly. So AE is equal to AE by delta X, AW is KW by delta X, and AP is equal to AE plus AW minus SPTP. B becomes S delta X. So far we have discussed about the intermediate node and how it is being converted, the differential equation, how it is being converted into a algebraic equation. Let us concentrate now at the boundary of the domain. All net transfer problems are fixed temperature boundary condition where TB is constant, or you have a constant heat flux boundary conditions where the flux is constant, or you can have a would also exist for the boundary nodes, which has to be converted into the algebraic form. So as shown in the figure, this first this slide shows constant heat flux condition. If temperature TB is constant, then there is no problem. But if there is a constant heat flux boundary condition, then we have to formulate QB indicates the flux coming in, which is known, minus QI is leaving from the ith phase towards the ith node, plus the source terms. Again, this boundary equation can be converted into AB, coefficient at the boundary into is equal to AI into TI plus a constant term, where AI is equal to KI upon delta. AB would be equal to AI minus SP into dx. Then we have converted the source term into a constant. Now this slide shows that we have slightly changed the, there is any ith node for which we want to find out the temperature Ti. It can be written the temperature of I minus 1th node plus the temperature of the I plus 1th node plus a constant term. First node, if we try to write down the equation for the first node, that is the boundary node. The boundary node. T1 would represent the temperature of the boundary node. This boundary node would have only one neighbor node, not so it will be a function of the temperature of the next node, T2. Then you go to the second node. Here we want to find out temperature T2. It will be a function of the temperature of the preceding node and the temperature of the following node that is moving ahead, T3. So temperature at T2 would be a function of T1 as well as T3. Similarly, temperature at would be a function of the, it will be called as tridiagonal because only the three diagonals would be having the coefficients and the rest of the coefficients would be taking the zero value, called as the matrix for the coefficients, A matrix. There will be another matrix, column matrix for the temperature, which will be equal to these multiple of these two matrices is going to be equal to the another column matrix, which comprises of the constant terms B's. So now we can arrive at a solution. Now you can very well measure T. One of the simplest method is you can simply inverse the matrix A. So B into A inverse provide you the value of the temperature. However, the Thomas algorithm is much simpler approach in which you need not to store n by n matrix. This Thomas algorithm provides a step-by-step solution. So in a one forward sweep from one end to the other end, then you take a reverse sweep from reverse to the forward end, and one or two sweep at a converged solution of the temperature. So we have seen how we have turned equations into algebraic equations. For those algebraic equations, now we have the preceding time steps. So we can, however, this scheme requires very small time step. Delta t needs to be very small, which is governed area, rho into delta x square upon twice k. Delta t should be less with certain weightages given to the temperatures. And this scheme is supposed to be unconditionally stable. It processes stable outputs. Besides this, you can have the 2D and the 3D formulations also. So far, we have studied only one-dimensional formulation. You can have a three-dimensional formulation. In that case, there are going to be 6 different nodes, neighboring nodes. Dimensional, there were 2 neighboring nodes. If you go for three-dimensional formulation, there are going to be 6 neighboring nodes. So on the screen, as you can see, find out, write down the algebraic equation for the temperature at node P in terms of the temperature at the neighboring node, TW, then temperature for the north node, south node, temperature for the top node or the bottom node, plus some constant. Again, from this equation, we can generate a diagonal matrix, and then that can be solved by using the iterative techniques, and that the Thomas algorithm cannot be used. So we'll have to assume some initial temperature field to calculate converged solution. So far we have studied how we can convert all these differences into algebraic equations, and then we can solve it for the flow fields, for the heat transfer application, and for the equations. Thank you. If anyone has any questions, please let me know. Hello. Okay. Again, it needs to be shared, na?
Yes.
Abhi, are you able to see? Present now, na? I have to press present now, na?
Present now. Then there will be one option, a window. And then click on a window. And click on your presentation and then share it.
Is it coming now?
No, sir. Just again press, just cross it. Just go to present now.
Just a minute, just a minute.
Yes, yes.
This PPT is coming. Now I share it.
Yes.
OneDrive. अभी तक तो आ रहा था ये.
No problem, sir. No problem.
Now it is.
Just cross it. Sir, just cross it once again.
Just a minute, just a minute.
Yes, sir.
Showing क्या है?
No, sir. Cross it. Now go to present mode. Click on the present now. A window. And there are a number of files over there. Then your presentation will be there. Cross it.
Window is visible.
Your window is visible. Then now window. Go a window. And there are files in which your presentation will be there. वहाँ एक बहुत सारे फाइल्स होंगे सर, उसमें आपका प्रेजेंटेशन होगा.
इसके ऊपर
हाँ, उस जो विंडो खुली होगी उसमें बहुत सारे प्रेजेंटेशन होंगे ना. आपका फाइल खुला होगा जिसमें प्रेजेंटेशन होगा.
ये तो विंडो बड़ी छोटी आ रही है.
हाँ, छोटी विंडो में होगा आपका प्रेजेंटेशन. उसमें क्लिक करिए आप.
देखिए नहीं.
कितने सारी फाइल है सर उसके अंदर. आवाज आ रही भैया, बाहर आ. अरे आ रही है. Sir, once again, go to present now.
अरे वो छोटी है.
हाँ, उस छोटी विंडो में आपका प्रेजेंटेशन होगा सर, उसी के ऊपर आपको क्लिक करना पड़ेगा. क्या नाम से प्रेजेंटेशन था आपका?
वो तो that is not visible at all.
नहीं होगा.
Is it coming?
No, sir.
Asha, let me tell you, there are one or two points which I would like to discuss more.
Yes, sir.
Not many things are left presently. Most of the things I think we have discussed.
Okay.
But let me know if anyone is having any questions. So,
Okay, sir. From participants, any question? Okay, then we will conclude, sir. Okay, sir. Okay, thank you, sir, for your informative session, and thank you very much. You explained very well on introduction to discretized and fruit flow, numerical prediction, the fruit film, importance of heat transfer in fruit flow, and there are some advantage of numericals on the, you described very well and excellently how discretization is done, and you described about trigonometrics algorithms. So thank you very much, sir.
Thank you.
Subodh, over to you. And all the participants, we will send you a feedback session. We will send you feedback from this session. Subodh, over to you.
Okay, sir. Thank you everyone for joining